Hi everyone, welcome to the section on logistic regression. This is our second section on the supervised machine learning, but first section on the classification because the previous section was on regression. So what we are going to cover in this section? So basically first we will cover the basic concept of logistic regression. So in this basic concept, we will see the definition of logistic regression. We will see what are our requirement of logistic regression, and we will also see how regression is different from the classification. Then we will discuss the limitations of linear regression. So in this topic, we will discuss why linear regression model cannot be used for the classification purpose. What are the limitations? Then we transform standard linear regression equation into the logistic regression equation. And then we will work on the loss function of logistic regression. We will see what is the loss function of logistic regression, which we are going to minimize during the classification. Then we will evaluate the performance of logistic regression by creating a very important matrix known as confusion matrix. So the confusion matrix is used to evaluate the classification of any classifier, whether it is a logistic regression or any other classifier. After creating the confusion matrix and after learning how to create the confusion matrix, we will calculate these four important metrics in order to evaluate the performance of logistic regression. So these are accuracy, precision, recall, and F1 score. So these are the four metrics. By using these four metrics, we will evaluate the performance of our logistic regression model. Then we will learn about the importance of this metric, which is receiver operator characteristic curve, in short known as ROC. So this is going to be our fifth metric in order to evaluate the performance of logistic regression. That is, after accuracy, precision, recall, and F1 score, we have ROC in order to evaluate the performance of logistic regression. Then we will implement all these learning in Python with the help of 6 projects. So I hope you will find this section very knowledgeable and interesting. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the basic concept of logistic regression, and we will also learn what are our requirements from the logistic regression or what we want logistic regression to do. So basically, logistic regression is used to perform classification, and classification is different from regression. So here is the comparison of regression and classification. So we can see that both are supervised machine learning algorithm. That is, we need labels in order to perform regression as well as classification. So the labels are present in both regression and classification. In regression, we perform the predictions of labels or target variables, and also in classification, we do the predictions of labels or target variables. Now here comes the big difference. In regression, the target variables are continuous. On the other hand, in classification, the target variables are discrete. Here are the example of few continuous target variables like a salaries or the housing price. On the other hand, we have the example for the classification. Suppose we have to classify between a disease, that is, a person has a disease or no, or we have to classify between different animals. So in that case, in regression, the target variable is continuous, and in classification, the target variable is discrete. So this is the big difference between the regression and classification, although both are supervised machine learning algorithm. So this is the example of a continuous target variable, and we can see that this is a continuous value, and we can see after the decimal, this value continues. So if we have to predict values like this, we need regression. On the other hand, the categories or the target variables in classifications are discrete, like yes or no. That is, whether the patient has a disease or no. On the other hand, whether the animal is a cat or a dog. So if our categories or target variables are discrete, basically then we are going to perform a classification. And if the target variables are continuous, then we will do regression. So both involve the prediction. In one case, the prediction is about the continuous variable. On the other hand, the prediction is about the discrete variable. So basically, what is logistic regression? So a logistic regression, also known as binary logistic regression, has logical target variables or labels. So basically, initially logistic regression was designed to perform the binary classification. When we say binary classification, it means it has two categories like yes or no, pass or fail, male and female. And we know that when we give these categories as an input to our machine, we have to transform them into integers. When we will transform them into the integers, we get 1, 0, that is 1 for yes and 0 for no. And similarly, we will get 1 or 0 for these and 1 or 0 for these categories as well. So basically 1, 0 are the binary numbers, or they are called the logical numbers. So in logistic regression, the word logistic comes from the word logical. Basically, when we perform logistic regression, we have the target variables that are logical, that is 0 and 1. So initially, logistic regression was designed to perform the binary classification, but now we can also perform the classification with more than two categories with the help of logistic regression. So basically, what logistic regression is doing? So logistic regression is doing classification. Now, the important concept is that it is a probabilistic classifier. Now, what does it mean? Basically, logistic regression returns the probabilities of class membership, and finally, we use a threshold to implement classification. Now, this is the example, and we have from 0 to 7, we have 8 data sample. Now, what logistic regression will return about these data samples? Suppose we have two classes in which we have to classify this 0 sample or the first sample. So logistic regression will return us the probability of the classes. So logistic regression is telling us that this first sample has 96.9% chance that it belongs to class 1, and it has only 3% chance that it belongs to class 0. Since the probability with class 1 is high, therefore the predicted class is 1. Here again, about the second sample, logistic regression is saying that around 45% it is likely belong to class 0, and around 55% it is likely to belong to class 1. In that case, the probability of sample 1 with class 1 is high, therefore the predicted class is 1. So in this way, logistic regression will tell us about the probability of each sample with respect to classes. So we have two classes and we have here samples. So if I see here, if I see the sample number 5, whose index is 4, we can see that this sample has around 58% chance that it belongs to class 0 and 42% chance that it belongs to class 1. So logistic regression is providing us the probability of this sample. So since the probability with class 0 is high as compared to probability of class 1, therefore the predicted class is 0. So what we do is that logistic regression is providing us the probabilities, and then we set a threshold. Now here the threshold is 0.5. If any of the probability is greater than 0.5, it means our data sample belongs to that class. So here we can see that this probability is greater than 0.5, and this is a probability with class 1. So our predicted class is 5 because this is greater than our threshold. So if anything is greater than 0.5, it will belong to class 1. This is our threshold. And if anything is less than 0.5, it belongs to class 0. Now here we can also see that this is the probability which is greater than 0.5, and this probability belongs to class 1. Therefore, this sample belongs to the first class, that is class 1. Similarly, if we see the last sample, so for the last sample, which is our 8th sample, the probability with class 0 is greater than 0.5, or it has high probability. On the other hand, the probability with class 1 is less than 0.5. So based on our threshold, we have decided that this last sample belongs to class 0. So this is the way in which probabilistic classifier like logistic regression works. And based on the probabilities with respect to classes, we have to predict the class. So I hope you understood this lecture. I hope you understood the concept of a logistic regression, that it is used to perform the classification, but while performing the classification, it returns the probability of the class membership. Then we set a threshold, and based on the threshold, we predict the class. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss what are the limitations of regression model and why we cannot use our regression model to perform classification and why we need logistic regression. So this is the regression line. So we have studied this regression, and this is a perfect regression line or regression model because it is predicting all the target values very well. And here there is no loss or there is no error. So here the predicted values and the target values are equal. So there is no error. In this line, we can see that the target values and the predicted values are not same everywhere. So we need to calculate the error. But before error, we can see that this is the equation of regression. This is called the standard equation of the regression. So this is our target value and this is the predicted value. So when the target and the predicted values are equal, there is no error. Otherwise, we have to calculate the error. So what are the limitations of this regression model and why we cannot use it for the classification? So consider this data set. We have a data set where disease depend upon the age. So this is our feature and this is our output variable, which is discrete. That is whether a person has a disease or it doesn't has a disease. So these are the samples. These are our data samples, or these are those patients who do not have the disease, and these are those patients who have the disease. So this disease depends upon the age. So we can see that for those points where the age is high, so if the age is high, it means that patient is more likely to have a disease. If we see here, these are the low age values. So if the age is low or less, it means those patients do not have a disease or they are less likely to have a disease. So this is a data set of a disease where the categories are yes and no. That is, they are discrete categories, or we can see that we will assign 1 to the yes and 0 to the no. So they are logical categories. Now, what happens if we want to classify this data with the help of a straight line? So this is our straight line. Now we can see that this straight line is starting and it is extended from here. And we know that if we know the slope of a regression line or our regression model, we can extend our regression line from minus infinite to plus infinite. Now, what is happening here? So this is our threshold. So any point whose probability will be greater than 0.5 or equal to or greater than 0.5, we will say that it belongs to class 1, that is, it has a disease. And if any of the sample will have probability less than 0.5, then it will belong to class 0. So see how this line or a regression model is trying to perform the classification and where is the problem. So this is our threshold value. Now let's see this point. If I move this point, or if I draw a straight line from this point to my regression model, and then I calculate the probability, I can see that it is less than 0.5. Therefore, this point belongs to class 0. It means this line has correctly classified this point. Similarly, for all these points, this line will work better and it will correctly classify. On the other hand, if I see these few points, their probability will be greater than 0.5 and they belong to class 1. So for these few points and for these few points, this regression line is performing well and it is classifying correctly. But about this point and this point, it is doing misclassification, because if I draw a straight line from this point or this data sample, this regression model is saying that its probability is greater than 0.5. Therefore, this should belong to class 1. So here is the misclassification because the actual label of this data sample is 0, and according to regression model, it should belong to class 1. So here is the misclassification. So what is happening now here? We can say that around 50% this line is doing well. That is, the accuracy of this regression model is 50% when we are using it for the classification. It is performing 50% correct classification and 50% approximately misclassification. Now the real problem comes here when the line is extended beyond this one and it is extended before 0 on this side. Now what is happening over here? What about this point? If I want to calculate the probability of this point with respect to my regression model, then if I draw a straight line from this point to the regression model, then my regression model is saying that its probability is greater than 1. Similarly, if I draw a straight line from this point to my regression model, then my regression model is saying that its probability is less than 0. We know that probability cannot be less than 0 and probability cannot be greater than 1. So here comes the problem with the regression model, that it is not giving us the correct values of the probability. And we know that the logistic regression is a probabilistic classifier. So we cannot get probabilistic classification from the regression model because it can assign the value of probability greater than 1 to a data sample, and also it can assign a value of probability less than 0 to the data sample. So for these 3 data sample, this regression model will assign the negative probability, and for these 2 data sample, it will assign the probability which is greater than 1. So that is the problem with the regression model, and that is the limitation of the regression model, that it may classify few point correctly and few point wrongly. But the actual problem is that it is not giving us the correct value of the probability about the membership of the data sample. So what is the solution? Now the solution, one of the solution may be to change the slope or to change the angle of this regression line. Now, if I use this line, it seems that this line is a bit better line than this, but the problem is the same. Even its classification performance is better. It will classify more point correctly as compared to this old red line. But again, the problem is same. If I have a point here, in that case, if I draw a straight line from this point to my regression model, again, I am getting the probability value which is greater than 1, so which cannot be accepted. So the problem is, whatever be the slope and whatever be the direction of the regression model, there will be points in a data set for which the regression model will not produce the value of probability that should be between 0 and 1. So it means the regression model is not giving us the true values of the probability for all the data points. Therefore, this regression model is not a probabilistic model. So here is the solution. So we need a model like this to define the probabilities of a class membership. We need a model which should not go beyond 1 or which should not go below 0. So we need a model like this. This is a solution. Since this is not related to the linear regression model, we can see that it has 3 different values of a slope. It is a slope here, then the slope here, and the slope here. So it has 3 different values of a slope. So this straight line from start to end is not our linear regression model. So this is the solution of the problem, and this line is not a linear regression model. Therefore, we need to use another model, which is a logistic regression. So we see how logistic regression can use this type of a model in order to solve the problem of probabilities. So in this lecture, we learn about the limitations of the regression model. We see that regression model can perform classification up to some extent, but it cannot return the probability of every data point between 0 and 1. On the other hand, we need this kind of model which should not go beyond 1 and it should not go before 0. So this kind of model we need to adopt, and we see how this kind of model fulfills the requirement of logistic regression. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in the previous lecture, we learned that we cannot use linear regression model to perform probabilistic classification. Therefore, we need to transform linear regression model into the logistic regression model. We also observed in the previous lecture that we need a model like this. So linear regression model cannot provide us this kind of a model. So how to get this kind of model in order to transform linear regression model into this kind of model? So luckily in mathematics, we have a function known as sigmoid function. So this is the shape of this sigmoid function, and we can see that its minimum value is 0 and its maximum value is 1. That is, it is ideally suited to perform probabilistic classification because its value ranges between 0 and 1, and the range of probability values is also between 0 and 1. So this is the mathematical representation of a sigmoid function. So we can see that if I put z is equals to 0, here I have written this function in the form of z. So we can use any variable in order to represent this sigmoid function. We can write it in the form of phi x, phi y, phi z, or we can use, or phi t. We can use any variable in order to write this mathematical form of the sigmoid function. So if I put z equals to 0 here, so it will become exponent raised to power 0. And we know that anything raised to power 0 will be equals to 1. So we will have 1 here and 1 here. We will get 2 at the denominator. So the total value will be half. It means when z is equals to 0, this function will give the value which is equals to 0.5. So 0 is the important point where we are getting 0.5 from the function. Now, if the value of z is negative, that is, it is less than 0, then we will get the value less than 0.5. And if we keep increasing the value of z towards negative direction, we can see that this function is approaching towards 0. That is, if the value of z is minus 10, at minus 10, its value is 0. Similarly, if we put the value of z which is greater than 0 in the sigmoid function, then we will get the value greater than 0.5. And if we keep on increasing the positive value, it means we are reaching towards 1. So for positive values of z, it will give us the values greater than 0.5. And for the negative values, it will give us the values less than 0.5. But its minimum value of this sigmoid function is 0 and the maximum value of this sigmoid function is 1. So this is an ideal situation, or this is an ideal function which can be used to transform linear regression model into the logistic regression model. So here we are going to perform the transformation of linear regression into a logistic regression. Now, this is my standard linear regression equation. So this standard linear regression equation is representing this straight line, which is in red color. Now, if I want to transform this straight line, or if I want to transform this linear regression model into the sigmoid function or into a logistic regression model, I need the sigmoid function. So this is the sigmoid function, and here I am using a variable y. So if I put this y, if I put the equation of linear regression here in the sigmoid function, then I will be able to transform it into the logistic regression. So we just need one step in order to transform a linear regression into a logistic regression. That is, in order to transform a linear regression into a classifier which can give us the probabilistic classification. So here is the logistic regression, and the output of the logistic regression is the probability of a class. So we can see that in the just performing the one step, we are able to transform linear regression into the logistic regression. Now, this is the equation of a logistic regression. So here P represent the probability of predicting the class or a target variable. Since this is the probability of the prediction, so I can replace this P by ypred, that is the predicted label, by the logistic regression model. Now just perform few mathematical steps. So I'm going to perform few steps. So I am moving this denominator from the right side of the equation to the left. So here is my value. So after this, there is only 1 which is left at the right side of the equation. Now multiply this y pred inside this parenthesis. So if I multiply y pred with 1, I will get y pred. If I multiply this y pred with this exponent term, I will get this term, and there is 1 at the right side of the equation. Now, after this, I am performing the step, that is, I am moving this y pred towards the right side of the equation so that it becomes a negative. So here we have moved this y pred to the right side of the equation. So it will become 1 minus y pred at the right side. So here is my left side. Now I am going to perform two steps simultaneously. That is, the first step is that I am moving this 1 minus y pred from right side of the equation to the left. So it will become the denominator of the left side of the equation. Similarly, I am moving this exponent term from left side of the equation to the right side of the equation. So when I will move this exponent term, its sign of its exponent value is changed. Previously, it was a negative sign, and now it becomes the positive sign. So this is my final equation for the logistic regression, where y pred is the probability of an event happening, and 1 minus y pred is the probability of an event not happening. Or we can say that y pred is the probability of predicting a class, and 1 minus y pred is the probability of not predicting a class. So we know that the probability of the events should be equal to 1 if we add their probabilities. So if I add y pred and 1 minus y pred, I will get 1, because this y pred is with positive sign and this y pred is with negative sign. So if I add this term with this term, I will get 1. So this is the representation of the equation of logistic regression. That is, logistic regression give us the probability of the class. So we have converted linear regression solution or problem into a logistic regression solution by placing linear regression into the sigmoid equation. So that was the key step, that by putting the standard linear equation into the sigmoid function, you transform linear regression model into the logistic regression model. So in logistic regression model, we will use a cutoff point of 0.5, that is, the threshold value or cutoff value is 0.5. So any data sample whose probability will be equal or greater than 0.5 will belong to class 1, and below 0.5, it will belongs to class 0. So in this lecture, we learn that the most important function is a sigmoid function, and we use that sigmoid function to convert linear regression model into a logistic regression model. So I hope you understood this transformation. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 1 on logistic regression. So basically in this project, we will learn how to get the class probabilities using logistic regression model. So here I am in my Google Drive. Here is my course material folder. Click on that folder. I have three major folders now: introduction, supervised machine learning, and unsupervised machine learning. Inside the supervised machine learning, I have logistic regression. Inside logistic regression, I have project 1. Let's click on this project to open it in our Google Colab environment. So this project has opened in Google Colab environment. So for this project, I need NumPy, I need pandas, and I have to import logistic regression from sk.learn_model. So let's run this cell to import all these necessary Python libraries. So the next step is to generate the data. So here I am generating a data. Basically, I am generating 12 samples of a data. So I have X, which is feature, and I have Y, which is target variable. If we see that the first 6 values of the target variable are 0, and the last 6 values are 1. So we have 12 samples, out of which first 6 samples belongs to class 0, and the last 6 sample belongs to class 1. Now, what this data is about? So basically, in this data, every value is the size of tumor in a patient. And with respect to size, we have assigned a label 0 or 1 to the patient. So this 3.77 is the size of a tumor of a patient. This 2.47 is also a size of a tumor of a patient. So here is the explanation of the data. X is the size of tumor. Labels are 0 or 1. 0 means no cancer and 1 means cancer. So the label 0 assigning to the patient, showing that this patient doesn't have any cancer, and 1 means cancer. Now let's change this data into a data frame so that we can understand it more clearly. So in order to convert the data into the data frames, I am using the function pd.dataframe. The first column is X, and in that column, I am passing the value of X. The name of second column is Y, and I am passing the value of Y in order to generate this data frame. So let's run this cell. We can see that the name X is not defined. So basically, first we have to run this cell, and now we can run this cell. Now we have X. We have 12 values for X from 0 to 11. We have 12 values, and we have 12 values for Y, and first 6 values are 0. It means if the size of a tumor in a patient is 3.77, it doesn't have cancer. On the other hand, if the size is around 6, it has a cancer. So 1 represent cancer presence and 0 represent the cancer is not present. Now it's time to apply logistic regression model on this dataset. That is to train the logistic regression model on our dataset. So the first step is, here I am instantiating this logistic regression because you see here, I have already imported it before. Now here I have instantiate the logistic regression, and I am called the variable as log_reg. Here I am fitting this variable to my data X and Y, and I am saving this into a variable LR, which is a logistic regression variable. Now let's run this cell. We have fit the data, but we get the error. Now what is the error? So error is telling that they are expecting 2D array, and we have 1D array instead. So what to do? So we have to, they are suggesting that you have to reshape data using -1 +1 in order to transform 1D into 2D. So they are saying that for logistic regression, we need to transform our X into 2D. So this is a requirement in Python for the logistic regression function. So let's check the shape or the dimension of our X. So X.shape here X is 12. So it is 1D. Now it's time to transform into 2D so that we can run it into a logistic regression function. So for transforming, we have to use X shape, reshape, X.reshape, and we have to use -1, 1. By doing this, I have transformed this X into 2D. Let's see X now. If I want to see X here, now we can see that X is in the form of column, and now it is in 2D, and we can also confirm it by again observing the shape of this X. So if I observe the shape of this X, we can see that now it is 12 by 1. It has 2 dimensions, that is 12 and 1. So we have transformed 1dx into a 2dx using a function reshape, and we are passing the inputs -1 and 1. Now it is in the format which require for the logistic regression function. Let's run this cell now, and we can see that we did not get any error. So the model has been trained on the dataset which has only 12 sample. Now it's time for testing the model and to get the probabilities and to get the prediction. Now, in order to test the model, I am generating a simple sample, only one sample, and the value of sample is 3.5. And here I am reshaping it so that I can pass it to the logistic regression model. We have seen that the requirement is to reshape the samples. Now, this is my unseen value. This is a single test sample. Now click on this in order to generate the sample. And here I am getting the predictions from my linear regression model that what is the probability that the given sample belongs to class 0 and class 1. If we go back, we can see that we have two classes, class 0 and 1. 0 means no cancer and 1 means cancer. Okay. Now it's time to get the probabilities. So the function is LR, which is linear regression model dot predict underscore prob A. That is the probability, the short form probability. And here I am passing my test sample. Let's run this cell to get the predictions. Now you can see that we are getting two values of probability, 0.54 and 0.45886. If I add them, they will be equal to 1. Now what this model is suggesting, the model is saying that it is highly likely that our test sample belongs to class 0 because its probability with class 0 is higher than with class 1. Let's confirm this by calling the function lr.predict and check the prediction. So here we are getting the label from the model and we are passing our test sample. Let's see the predicted label. So the predicted label is 0, which is in accordance with the probabilities. It means our logistic regression has produced correct values of the probabilities for both class 0 and class 1. So the probability of this test sample is high with class 0. Therefore, this test sample belongs to class 0. And we have confirmed this with this calculation that it belongs to class 0. So the sample value is 3.5. If we go back, there is no 3.5 in our data set. But if we see, this 3.5 is between 3.7 and 2.4. It means its value is in between and its label should also be 0, which is verified by calculating the probabilities and also by getting the predictions. So in this way, in this lecture, we learn how to find the probabilities of a test sample using the logistic regression, and from the probability, how to decide that which class this sample belongs to, and then we will confirm by calculating the class predictions. So I stop this lecture here and I will continue this project in the next lecture. See you there. Hi everyone, welcome to this lecture. So this lecture is a part 2 of project 1. So here we will continue our project 1. So what I am going to do in the second part of the project 1, so basically I am again getting the class probabilities from my logistic regression model, but this time I am using another data set. So this time I am generating a data set using a function make_classification. I am importing this function from sklearn.dataset. The other thing is I also need train test split, which I am importing from sklearn.model_selection. So let's run this cell to import all these necessary functions. Now here is the important thing, that I am going to use a function make_classification. So what are the inputs? So there are quite a few input to this function. First of all, how many samples I need in my data set? So here I am generating a 50 samples. Then how many features I need? Here I am generating a data set with 2 features. How many of the features should be informative? So I want all my 2 features should be informative. So there should be no redundant feature in my data set. Therefore, I have passed number of redundant is equals to 0. And here number of classes is equals to 2. So I want 2 classes in my data set. So if I run this cell, I will get 2 output. That is, I will get the value of the features and I will get the labels from this data set. So if I run this cell, I will get X and Y. If I run this np.unique, so I want to see how many unique labels this data set has provided me. So let's run this cell. So we have 2 labels, 0 and 1, because we have passed number of classes is equals to 2. So I get 2 labels. Now to check the shape of our feature, which is X, so it is 50 by 2 because we have 50 samples and we have 2 features. So the thing is, the important thing is this make classification function is generating data set randomly. So every time I run this cell, I will see different values of X. So I can confirm this, that if I add another cell and I want to see the value of X, so in order to see the value of X, let me reduce the number of samples to 5 so that I can learn how make classification is producing data sample for me. So I am now creating 5 samples and here is the value of X. So you can see that here the value of X of the first feature is 0.69 and the second feature is 1.71. So if I run this again and I want to see X, you will see these values will be changed. Let's run this cell. So all these values are changed. So what is happening over here? The one thing is happening that make classification is generating data randomly. So every time I will run this function, I will get the different samples of my data. That is the different sample of my features. If I want that every time I run this cell, I want to see the same samples, I have to pass a seed which is in the form of random state. Okay, if I run this cell again, you can see if now I will run, these values will be changed. So if I want every time that same value should be produced, so I have to pass a random state, random underscore state, and I have to pass any of the values. Suppose I am passing 42 here. Now I have passed random state is equals to 42. If I run this cell now, and I will see x. So now you can see that it is 1.26 and minus 1. Now, if I run this again and again, the value of x will not change and I will get the same samples. So let's run this cell again and see the value of x. Now you can see it is 1.26. Again, if I run this cell and again see the value, so we can see that it is 1.26. So now, since I initially needed 50 samples, therefore I am back to my original data set, and here is the random state, so that I have passed the random state for you student, that whenever you run this, you will get the same values which I get. So the random state is equals to 42. Now run this cell, and if I run this, so I have these 50 value of samples, because if I run this, I have 50 samples and I have 2 feature. So this is the advantage of make classification. Every time you run this, you can get the different data set, and if you want the same samples to be produced every time, you have to pass a random state is equals to 42. So that is the description of the function make classification. Now I have my data set generated. Now it's time to perform a train test split. So for train test split, there is a function train underscore test underscore split. I have to pass my feature, my labels, test size, and random state again 42, so that every time I run this cell, I get the same feature, same samples in the training and the testing component. So when I run this cell, I will get 4 output: the training samples, testing samples, training labels, and the testing labels. Okay, now it's time to train a logistic regression on our training component. So here I am creating a logistic regression. I am instantiating my logistic regression and I am calling it a model. Here I am fitting the model on my training component of a data. Basically, here I am training my model. So dot fit is used to train the model. So let's run this cell. Here I am generating the probabilities from X test. So let's run this cell. So we know from the part 1 of this project that the function used for generating probabilities is lr.predict underscore prob a. This time we have 10 samples in our test data. So these are the probabilities of the values with respect to X test. So we can see that these values are 6.17 exponent minus 2. So these are with the different exponents. So what we can do here is that we can call it round 2, so that we can see it into after 2 places of decimal. So if I run this cell, okay, now it is very clear. So we have transformed these probabilities into 2 places of decimal. That is, we need a value 2, or we need 2 values after the decimal point. So we can see that if we see the first sample, now the probability of first sample with class 0 is 0.06 and with class 1 is 0.1. It means our first test sample belongs to class 1. Now here is a very high value of the probability. So our second sample belongs to class 0. Our third sample belongs to class 1. Fourth sample belongs to class 1. So, and our last sample belongs to class 0. So these are the probabilities with class 1. The first column of this probability indicates that the probability with respect to class 0, and this belongs to class 1, because we have 2 classes. If we go back, we can see that we have classes 0 and 1. Okay, so let's confirm whether these probabilities values are correct or not. Let's get the class predictions. So we can see that the first sample belongs to class 1. It has high probability with class 1, which is also verified from the class prediction. And the last sample belongs to class 0. It has high probability with class 0. It is also verified with this. So what we can do further in order to get these probabilities more clear and get the more understanding of the probabilities and the predictions. Okay, we can create a table. We can create a table of 3 columns. So in the first column, we will have this value of the probability. In the second column, we will have this value of the probability. And in the third column, we will have prediction, and then we will compare. So I am creating a table using pd.dataframe. So I am creating the data frame using the commands pd.dataframe, where pd stands for pandas, or it is representing pandas library. So my first column name is probability underscore class 0. Second column name is probability underscore class 1. And the third column name is the predicted class. So in the first column, I am passing the first column. So if I write this y underscore pred underscore prob is to 0, so this will give me the first column. So we can confirm this. If I write a code here, y pred underscore prob 0, so what will happening? it is giving me the value of the first column, 0.01, you can see, then 1, then it is 0.0. So if I want to extract first column, so I have to pass this column. This column means all the rows I needed, and 0 means I need the value from the first column. So this is the first column of ypred_prob, and we know that the index in Python starts from 0. Therefore, in order to extract this first column, I have to pass 0. So if I pass 1 here, then I will get these values. The first value will be 0.94 and the last value will be 0.03. So we can see that our first value is 0.94 and the last value is 0.3. So in this way, I can get any column. That is, there are two columns in this probability matrix. So if I want to extract first column, I have to pass 0 here. And for second column, I have to pass 1 here. So I am doing the same here. For getting the probabilities related to class 0, I need the first column of ypred.prob. So I am passing a 0 here. And for getting the probabilities of class 1, I need the second column. Therefore, I am passing ypred_prob equals to column, and this is 1. This column means I am getting all the rows, and this 1 means I am getting the second column from here. The last column name is predicted class, and I am passing these values. So let's run this cell and see the table. So we will get more understanding now because we have created the table. If you see this column, prob_class 0, if you see this column of the table, it has all the values related to class 0 and it has all the values related to class 1. So these values are taken from this and this value. And here is the predicted class. So we can confirm there, when the probability related to class 1 is high, our prediction about the class is also accurate. That is, when the probability related to class 1 is high, the predicted class is also 1. When the probability related to class 0 is high, the predicted class is also 0. Similarly, we can see here the predicted probability with class 1 is high. So the prediction class or predicted class is also 1. It means our model has calculated all the probability values correctly, and it is confirmed with the predicted class. So in this lecture, we learn about the probabilities which are produced by the logistic regression model. We learn how to calculate the class probabilities, and we also learn how to verify these class probabilities with the help of predicted class. So that was the lecture 2 on project 1, where we again learn how to calculate the class probabilities. But in this part, we use a different data set and we learn how we can create our own data set using a function make_classification. So I hope you understood this part of the project 1 as well. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss the loss function for the logistic regression. Now, in order to create the loss function, the first step is to calculate the error. So error is the difference between the target value and the predicted value. After calculating the error, we square the error and then take the mean. So this kind of loss function is known as mean square error. So we will try to create the mean square error because it is a convex loss function. And we know that if our function is convex, then it is easy to get the global minimum value. But if we see here, this is the predicted value for the logistic regression. So in this prediction, we have seen an exponent equation. So this exponent function is nonlinear. So what will happen when I put this predicted value here? I will not get a convex function, but I will get a bit complex function. Now, if I put this yPredict here and solve for LW, I need a complex mathematics in order to simplify the loss function for the logistic regression. So basically, we create loss function so that we can reduce the error and we can optimize the weights and bias of the model. So if I put this yPredict here and simplify, I will get this equation. So this is the equation of a loss function for the logistic regression, and we can see that it is for n number of samples. Here there is a negative sign. Here there are a number of samples which are n. So we will take summation from 0 to n minus 1. This yi is the target value of the is sample. This is the predicted value, and here there is a log. Then there is a second term. Here there is 1 minus yi. This is again the target value, and this is the predicted value. So we can see that we have a log, we have the target value, we have the predicted value, and we have to add all of them. So this is the loss function for the logistic regression. Now it seems that this loss function has so many terms, but the thing is it will not work simultaneously, or both terms of the loss function will not work simultaneously for all kind of labels. Suppose we have a binary classification problem and our label is 1. So when y is equals to 1, we can simplify this loss function very easily. That is, put y is equals to 1 here and put y is equals to 1 here. So what will happen? If I put y equals to 1 here and y equals to 1 here, so this term will wipe out, or this term will become 0, because 1 minus 1 is equals to 0, and I am left with only term. Here I have removed these number of sample term so that I can get the understanding. So I have a negative sign and I have a log y pred I. It means this equation will be reduced to this simplified form if y is equals to 1. That is, we are not using this whole loss function equation for all the labels. For y is equals to 1, we will use only the first component of the loss function, and we have proved that if y is equals to 1, the second term will be 0, and we will get minus log y pred of I. So this short equation, or this reduced equation, will be used to calculate the loss function if our label is 1. On the other hand, if our label is 0, we can also get the simplified form of this loss function. When y is equals to 0, so we can put y is equals to 0 here and y is equals to 0 here. So this 0 will make everything 0 here, and then we get this negative sign, and we get this log 1 minus y pred I. So 1 minus 0 is 1, and then we get this term. It means when y is equals to 0, we again getting the simplified form of the loss function. Basically, now we are getting the second component of the loss function. Now, what will happen? If we want to reduce this loss function, then we have to differentiate it with respect to parameters. So the parameter of the model are the weights. Suppose if we have weights, m number of weights, that is 0, 1, 2, 3, and we have m number of components, it means I have to take the partial derivative of this loss function equation with respect to weights. And then I will calculate this ratio, which is known as gradient. So in the gradient descent lecture of linear regression, we know that this term is known as the gradient. So after calculating the gradient, we will multiply the gradient with the learning rate, and then we will subtract this term from the old value of the weight in order to get the new value of the weight. So in this way, when we put labels y is equals to 1 or y equals to 0, we will get the simplified form of the loss function, where we can perform the gradient descent. We can easily take the gradient of the loss function, and then we can perform the weight adjustment. So in this lecture, we learn how to create the loss function for the logistic regression. We have also learned that the whole loss function of the logistic regression will not be used for all the labels. For y is equals to 1 and for y equals to 0, we will have the simplified form of the loss functions. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we learn how we can evaluate our model using a matrix known as confusion matrix. Now, we have already transformed a linear regression problem into a logistic regression problem. We have already learned about the loss function of the logistic regression model. Now it's time to evaluate the model using confusion matrix. So basically, we made a confusion matrix from the testing samples of the data. That is, we split the data into training and testing. Then we train our logistic regression model on the training component of the data. And then we evaluate the model on a test data. Using test data, we create a confusion matrix, and then we evaluate the performance of logistic regression classifier based on the confusion matrix. So how to construct a confusion matrix? So this is a confusion matrix of size 2 by 2. Its size is 2 by 2 because we have two labels, no and yes. So one of the important thing of the confusion matrix is its size. So the size of the confusion matrix depends upon total number of labels or target variables. So if we have two labels, the size of confusion matrix will be 2 by 2. If we have three labels, then its size would be 3 by 3. The other thing about the confusion matrix is that it is a square matrix. That is, rows and columns are same. So the size of the confusion matrix is either 2 by 2, 3 by 3, 4 by 4, 5 by 5. So it will be a square matrix. The third thing about the confusion matrix is that it has also the axis. This is the vertical axis of the confusion matrix, and this is the horizontal axis of the confusion matrix. These are the four elements of a confusion matrix. So in this case, we have a confusion matrix of size 2 by 2 because we have two labels. Now I have a testing samples equals to 215. Now with the help of these 200 testing sample, how the confusion matrix will be created by the model during the testing. So basically, if we see, it has divided these 215 samples into four elements. Here we have 50, here we have 10, we have 5, and we have 150. Let's understand each element separately. So this 50, what about this 50? This 50 is at the intersection of two things, that is actual no and predicted no. So what does it mean? It means these 50 samples are those whose actual label is no, and model is also predicting no. So these 50 samples are correctly classified by the model when they were actually no, that is they belongs to a class no or they belong to the negative class, and the model also classifying them as a negative. So it means these 50 are the correctly classified sample. Now look at these 150 samples. So they are at the intersection of actual yes and predicted yes. It means these 150 sample belongs to a class yes or belongs to a positive class, and model is also predicting them as a yes or as a positive class. It means these 150 samples are also correctly classified by the model. So these 50 and these 150 which are present at the diagonal of this confusion matrix are those number of samples which are classified correctly by our model. Now what about this 10? So here is a value 10, and we can see that this 10 value is at the intersection of actually no and predicted yes. So what is happening over here? Basically, these 10 samples belong to negative class. So in reality, these 10 sample belongs to a negative class, and our model is saying that they belongs to a positive class or a yes class. So these 10 samples are wrongly classified sample. Similarly, these 5 samples are also wrongly classified sample. That is, actually they belong to a positive class, that is yes, and model is saying that they belong to a negative class. So model is not predicting these 10 and 5 correctly. It means out of 215 samples, these 50 and these 150 samples are correctly classified by the model. On the other hand, these 10 and these 5 samples are not correctly classified by the model. It means now with this information that these two samples are correctly classified and these two samples are not correctly classified, we can easily discuss the accuracy of the model. That is, the total samples are 215. So out of 215, 200 samples are correctly classified and 15 samples are not correctly classified. It means if I divide this 200 by total of 215, I will get the accuracy of model. So in this way, from the confusion matrix, by observing the correctly classified samples and the wrongly classified sample, we can easily calculate the accuracy of a model using confusion matrix. So here we can see that if I want to calculate the accuracy with the help of this confusion matrix, so I have total correct guesses or total guesses. So total correct guesses are 150 over 150. This is the correct guess because it belongs to negative class, and model is also saying that it belongs to a negative class. This is also correct guess because it belongs to a positive class, that is class whose name is yes or a positive class, and model is also saying that it belongs to a positive class. So these are two the correctly classified samples. So we divide them, we add them and divide by the total number of guesses. So we get 0.93 accuracy. And if we transfer into the percentage, they will be 93%. Now every element in the confusion metric has its name. So here are the name of these elements. So this 50 or this part or this element of the confusion matrix is called true negative. This is called false positive. This is called false negative. And this is our true positive. So these are the four names of the elements present in a confusion matrix. Now, name is defining everything. This is true and these are negative. So basically, these 50 samples belongs to negative class and model is predicting them truly. Similarly, these 150 samples belongs to positive class and model is predicting them correctly or truly. On the other hand, these 10 samples basically belongs to negative class. So model is saying they belongs to positive. So model has classified them as a positive, which is false. So that's why it is known as false positive. Look at these 5 samples. So these 5 samples actually belongs to the positive class, but model is saying that they belongs to the negative class or the class whose name is no. So model is predicting them wrongly or falsely as a negative. That's why they are called false negative samples. So these are the 4 important names of the elements which are present in the confusion matrix: true negative, false positive, false negative, and true positive. So the false positive and false negative, the samples belongs to these categories are wrongly classified. So basically, these two values are the error of the model. Here the model is correct. There is no error when we have only true negative and true positive. On the other hand, false positive is an error and false negative is also an error. So these are the definition of true positive and true negative. A true positive is an outcome where the model correctly predicts the positive class. Similarly, a true negative is an outcome where the model correctly predicts the negative class. So both these true positive and true negative indicates those samples which are correctly predicted by our model. On the other hand, we also have false positive and false negative. So a false positive is when a model predicts positive when it is not a positive or it is negative. False positive is also known as type 1 error. So we have to remember this name as well. Since we have already learned that false positive is an error, now the name of this error is known as type 1 error. Similarly, false negative is also an error and the definition is when a model predicts negative when actually it was positive. So false negative is also an error and it is known as type 2 error. So we have to learn about this type 1 and type 2 error. We have to remember the name of type 1 and type 2 error. So in this lecture, we learn about the confusion matrix. We learn that we can create the confusion matrix and the size of confusion matrix is equal to the number of target variables. So if we have two target variables, no or yes, or a negative and a positive target, in that case, our confusion matrix will be 2 by 2. So inside the confusion matrix, we have 4 important terms named as true positive, true negative, false negative, and false positive. So true negative and true positive are those samples which are correctly classified by the model, whereas the false positive and false negative are those samples which are wrongly classified by the model. Therefore, these two are called the errors of the model. False positive is also known as type 1 error and false negative is also known as type 2 error. So I hope you understood this lecture. Thanks for listening and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the 4 important metrics that can be used to evaluate the performance of any classifier. So these metrics are accuracy, precision, recall, and F1 score. So in the previous lecture, we learn about the confusion matrix and we calculate the accuracy from the confusion matrix. So we can see that we can easily calculate the accuracy of a classifier if we have a confusion matrix, because the accuracy is the ratio of correct classification divided by the total number of classifications. So we have already calculated the accuracy from the confusion matrix. So in this lecture, we will also learn about 3 more metrics other than the accuracy. These are precision, recall, and F1 score. And we will see how we can calculate these matrices with the help of confusion matrix. So like accuracy, we will calculate precision also with the help of confusion matrix. Similarly, recall, will also be calculated with the help of confusion matrix, and F1 score will be calculated with the help of precision and recall. So let's start study each of them. The first important metric is the accuracy. Accuracy is the most intuitive performance, and it is simply a ratio of correctly predicted observation to the total observation. So we can see that in accuracy, we have a ratio of total correct guesses over total guesses. And we see in accuracy, we use every element of the confusion matrix, that is true positive, false negative, and true negative. So in this way, we can calculate the accuracy of a model and we can measure the performance of the model. But there is an accuracy issue. There is an issue with the accuracy if the data set is biased. Bias means if the labels are not equal. The situation is that if we have a data set with only 1% positive label and 99% negative label. So what will happen in that case? In that case, if the model decide to predict everything as a negative, it will still have a 99% accuracy. So what does it mean? If I give a test sample to a model and that test sample is a positive labeled sample, but model has decided that it will produce a negative prediction for any kind of input, even then its accuracy will be 99% correct. So in that case, if the data set is biased, accuracy is not the exact or precise representation of the performance of a model if the data set is biased. In that case, we need another matrix which is known as precision. So the problem with accuracy comes when the data set is biased and we have approximately 99% negative labels. In that case, what model can do? Model can cheat us if model has decided to predict everything as a negative, even then its accuracy will be 99%. In that case, accuracy is not a true representative of a model performance. So we need a precision in that case. So what is precision? In precision is the ratio of correctly predicted positive observation to the total predictive positive observation. Here, there are total positive guesses and how many of them are correct. So this is the ratio of precision. So in precision, the numerator quantity is a true positive and the denominator quantity is the sum of true positive and a false positive. So sum of these two quantity become the total positive guesses, and how many of them are correct, that will give us the value of precision. So precision solve the issue of accuracy with biased data. So if your model is classifying everything to negative, now its precision is 0. So in precision, there is nothing about the negative class. All the classes or all the components are positive. So if our model has decided to predict everything as a negative, its precision is 0. So what is happening right now is that after calculating the accuracy, it is important to calculate the precision, especially if the data is a biased data where the labels are not equal in number. So in that case, the accuracy will not be a true representative, but we have to calculate the precision as well in order to avoid the misleading that can come from the value of accuracy. Now there is also an issue with the precision. So the precision does not paint the entire picture. It will not tell you anything about the negative labels. So if we see in the precision equation, all the labels are positive or all the information is about the positive guesses. So there is nothing about the negative labels. So what will happen in that case? In that case, precision can be defeated by a classifier if it just makes one correct positive guess and does not make any more predictions, then the precision is 100%. So what happens if model predict a one correct positive guess? That is the true positive. And after that, it stops predicting anything. In that case, the precision is 100. So what happens if this value is 1 and this value is also 1? That is, our correct positive guesses and total positive guesses are equal. In that case, precision will be 1, and in terms of percentage, it will be 100%. So if we have only one sample, if we give one sample to the model, or basically if model predict just one sample and then it stops doing any further prediction, in that case, that one sample will be the correct positive guess, and that will also be the total positive guess. In that case, this ratio will be 1, and we get the value of precision equals to 1, and the percentage value will be 100%. So there is also an issue with the precision because it is not telling anything about the negative label, especially the false negative. So this issue is solved by another metric known as recall. Now look at recall. Recall is the ratio of correctly predicted positive observation to all observation in actual classes. So basically, if we see, there is a one element different in recall as compared to the precision. In precision, we have false positive value here, whereas in recall, we have a false negative value here. So basically, actually, this value is a positive value, but model has classified it wrongly as a negative. So that's why we call it that the sum of true positive and false negative is basically a total positive labels. So out of total positive labels, how many labels are correctly classified or guessed by our model? It will give us the value of recall. So if we see the equation of precision, here we have total positive guesses, and in recall we have total positive labels. So that is the difference, and we can see that here also the false negative label is taken into account. So it solves the problem of just making one correct positive guess. So now if our model is only giving the value of TP or a true positive, and it is not giving any false negative, that is, if a classifier make only one correct positive and the rest of all are negative, then in that case this quantity will become so large as compared to this that our recall value will be nearly equal to 0. So the problem of the precision is now solved with the recall because we have added the representation of negative labels as well. Now recall is different as it takes the negative label into equation. It asks how many. So this is the definition of recall. It asks how many positive labels you found out of all the positive label that is exist. So this is the definition, that how many true positive and how many positive labels you predict correctly out of the total available positive labels. Now there is an issue with the recall. If classifier predicts everything as a positive, then recall will be 100%. That if we pass 100 sample to the classifier and it is giving every sample as a true positive, now in that case recall will be 100%, which is not a true representative of a classifier. That is, if false negative is 0 and everything is classified as a positive label. Previously in the precision, the problem was that model decided only one correct positive. Now the problem with the recall is model is classifying everything as a positive. In precision, model classify one sample as a positive and then it stops doing prediction further. But in case of a recall, it classify everything as a positive. In that case, there will be no false negative term, and the ratio will be 1 in case of recall as well, and we will get the 100% recall. So we do not need 100% recall, 100% precision, neither we need 0 recall or 0 precision. In that case, in order to avoid this problem of recall and precision, we need the fourth metric, which is F1 score. So F1 score is the most important metrics because if any of the recall and precision is 0, your F1 score is 0. So this is the equation of F1 score, and we can see that in the numerator, we have the multiplication of a recall and a precision, and then we have multiply by 2, and here is the sum. Now in multiplication, if any of the recall or the precision is 0, our F1 score will also be 0. So that is, F1 score is more important than the accuracy, whether our data is a biased or unbiased. So we can see that F1 score is the weighted average of precision and recall. This score takes both false positive and false negative into the account. Intuitively, it is not easy to understand as accuracy, but F1 is usually more useful than accuracy when you have uneven class. So if you have uneven class distribution, that is, you have a biased data, in that case, F1 is more important. F1 score is more important than the accuracy. So accuracy works better if false positive and false negative have similar cost. That is, you have similar numbers of false positive and false negative. That is, your data is balanced or it is unbiased. On the other hand, if the cost of false positive and false negative are different, it's better to look at the precision and recall. And finally, it's better to calculate the F1 score. Now, this was our fourth metric after accuracy, precision, and recall. And we can see that it is important because it is taken into account everything. It is taken into account recall and precision. If any of the value is 0, it means F1 score will be a 0. So this F1 score is very important. It represents the true performance of a model classification, whether your data is a biased or an unbiased. Now, in F1 score, we are using harmonic mean, so it punishes the extreme values more. The thing is, if a classifier with precision 1 and recall 0 will have 0.5 arithmetic mean while 0 harmonic mean. So this equation is called the harmonic mean of recall and precision. Now, why it is important? Because if any of the recall or precision is 0, its harmonic mean is 0. But on arithmetic mean is different. Arithmetic mean will be the sum of precision and recall divided by 2. It is like the mean of two numbers. Like if I have two numbers A and B, so the arithmetic mean will be A plus B divided by 2. Similarly, the arithmetic mean of the precision and recall will be precision plus recall by 2. So what is the disadvantage with the arithmetic mean? So if we have a recall 0 and precision 1, or we have a precision 0 and recall 1, we will still get F1 score 0.5 if we use arithmetic mean. Therefore, we are avoiding arithmetic mean and we are penalize our model more if any of the precision and recall is 0. Therefore, we are using the harmonic mean in order to calculate the F1 score of the model. So in this lecture, we learn about these four important metrics which are used to evaluate the performance of a classifier. We can see that we need confusion metrics in order to calculate accuracy, precision, recall, and F1 score. We also learn that the F1 score is more important metrics. It will give you the more better representation of the model performance because it is taking into account everything, that is precision, recall, and it works equally well whether your dataset is unbiased or a biased. If your dataset is unbiased, in that case, accuracy also works well. But in the case of biased data, accuracy is not giving us the true picture about the model performance. So for that unbiased data, we need to calculate precision, recall, and F1 score. So what we will do basically, now for any kind of dataset, it is important to calculate all these four metrics. So I hope you understood the concept behind accuracy, precision, recall, and F1 score in this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn another important metric that can be used to evaluate the performance of a classifier. This metric is known as receiver operator characteristic curve, or in short, we can call it ROC. So what is ROC? So ROC is the curve between false positive and true positive. So basically in ROC, we only use the positive labels predicted by the model. So the false positive labels are also predicted by the model and the true positive labels are also predicted by the model. So ROC curve is between the false positive and the true positive. Area under the ROC curve indicate the precision of the model. We know from the definition or from the equation of the precision that the equation of precision is true positive divided by true positive plus false positive. So precision addresses only the positive samples predicted by the model. Therefore, the area under the curve will indicate the precision of the model. So if we see this curve, we can see that AUC here, AUC is area under the curve. So its value is 0.8. It means this ROC is for the model whose precision is 0.8 or 80% because area under the curve of ROC represent the precision of the model. On x-axis, we can see that we have a false positive rate, and on y-axis, we have a true positive rate. So it means it is the curve between the false positive and true positive, and the area under this curve indicates the precision of the model. So this is another example of ROC for a different classifier whose precision value is small, that is less. This is 0.52 or it is 52%. So we can see that this is not a perfect straight line. We can see that straight line here, and after this point, the slope of the line is changing. So this ROC represent a classifier whose precision is only 52%. So from this straight line or this kind of straight line or this ROC, we can learn one important thing is that if the precision of the model is 50%, then in that case, we will get a straight line which will divide this curve equally, that is into the true positive rate and into the false positive rate. This is another very important ROC of a model whose accuracy is 100% and especially the precision is also 100%. We can see that the area of the area under the curve is 1, that is 100%, and area under the curve represent the precision value of the model. So we can see that there is no false positive. That is, our model is predicting every label correctly and there is no misclassification or there is no wrong classification. So we can see this is a line or this is a curve of a model whose precision is 100%. So in this lecture, we learn another important metric which is known as ROC. After calculating and learning the 4 metrics in the previous lecture, that is accuracy, precision, recall, and F1 score, we can see that there is another matrix known as ROC. So ROC is basically the curve between the positive labels predicted by the model, that is between the false positive and the true positive, and the area under this ROC curve represent the precision of the model. So I hope you understood the concept of ROC. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this is project 2 on logistic regression. So in this lecture, basically we will implement project 2 on logistic regression. In project 2, we will learn how to evaluate the performance of logistic regression. That is, we will calculate the confusion matrix, we will calculate accuracy, precision, recall, and F1 score, and we will also plot ROC curve. So here I am in my Google Drive, and inside my Google Drive, there is a folder course material. Click on this folder, and inside this folder, I have a folder known as supervised machine learning. Click on this folder, and here it is a logistic regression folder. Inside the logistic regression, I have project 2 evaluating logistic regression. If I click on this, it will open in Google Colab environment. So here I am in my project 2. So for project 2, I need NumPy. I need a function make classification, which I will import from sklearn.datasets. Similarly, I will import logistic regression from sklearn.linear_model. I need plain test split, which I will import from sklearn.model_selection. I need matplotlib. I need pandas. So let's run this cell in order to import all the necessary libraries of Python. Now, the second step is that I am going to create my own data set. Now I am using the function make_classification. Now this is a very good function. It helps us to create our own data set. So what are the input to this function? First of all, I can control the number of samples. So here I am passing number of samples is equals to 200. Now it's up to me whether I want to create 200, 500, 1000 or 2000 sample. So the first input is number of samples. Second input is number of features. Here I want to create 2 features with 200 samples. I want all the features to be informative and I do not want any feature to be redundant or multi-collinear. Therefore, number of redundant feature is 0. I want number of classes is equals to 2. So I want a binary classification. Therefore, I am producing a data set with number of classes is equals to 2. Random state is equals to 42. So I am passing random state is equals to 42. So the advantage of passing random state is that every time I run this cell, I will get the same kind of samples, same samples basically, because the make classification generate the data randomly. If I did not pass random state equals to 42 or random state equals to any other value, it will generate different samples every time I run this cell. If I want same samples to be generated, I have to pass random state equals to some of the value. Here I am using 42. So let's run this cell. So what is happening? This make classification will give me 2 output, X and Y. X are my features and Y are my target variables. So if I want to check the shape, X dot shape, it is 200 by 2 because I have input number of samples is equals to 200 and my number of feature is equals to 2. Therefore, it is 200 by 2. Now I want to check my unique labels. Here I have passes number of classes is equals to, these are basically the labels or the target variables. So if I use np.unique, I want to see how many unique labels I have. So I have 2 classes and the labels are 0 and 1. So in this way, using make underscore classification function, I have generated my own data set and I have seen the size of my feature, which is 200 by 2. And I have seen that I have 2 discrete labels 0 and 1. Now it's time to perform a train test split. Here is the function train underscore test underscore split. So this function need quite a few input parameters. The first is x, that is feature. The second is a target variable, then the test size, and here is a random state equals to 42. So the test size I am using is 0.2. It means out of 200 samples, I am using 20% as a test and remaining 80% as a training. Random state equals to 42. Again, I want that every time I split the data, I should get same number of samples. Okay, let's run this cell to perform train test split. Here I want to see the shape. So out of 200, 160 samples will be used for training and rest 40 will be used for the testing. Now it's time to apply logistic regression. So the first step is that I am going to instantiate logistic regression and I am calling it model. Then I am fitting this model on my training component of a data, that is X train and Y train. So here I have completed the training of the model from the training component of the data. Now it's time to get the probabilities and prediction from X test. Since our model has been trained on the training component, now it is ready to give the probability predictions. So for probability predictions, I am using lr.predict underscore prob A. And here I am passing the testing component of my data. So if I run this cell, I will able to see the probabilities. Let's run this cell. So here I have 40 test sample and I am getting the probability of each sample with respect to class 0 and class 1. If I see first sample, so probabilities are telling me that its chance with class 0 is only 0.03. That is, it is 3% likely that first sample belongs to class 0, and it is approximately 97% that it is with class 1. So according to these two probability values, it means the first sample belongs to class 1. So in each row, one thing is common, that is, if I add these two values, that is probability with class 0 and class 1, I will get the sum equals to 1. So the sum of this value and this value is also 1. So the sum of the two values which are present in a row is equals to 1 because these are the probabilities with two classes. If we go to the next sample, it has high probability with class 1. Similarly, if we go to the fifth sample here, it has the high probability with class 0 as compared to class 1. If we go to the last sample, we can see that our last sample belongs to class 0. It has high probability with class 0 as compared to class 1. Now it's time to confirm this. These are the probabilities. Let's get the class predictions. So for class prediction, I am using lr.predict. Here I am getting the class predictions directly from the test data. So I can confirm that my last sample belongs to class 0. Here is the confirmation. Similarly, if I want to see all the 40 samples with their probabilities and class prediction, I have to make a table of these probabilities and these predictions. So for this, if I want to observe them in a single table, I am using pd.dataframe. That is, I am using a function dataframe from pandas. So I am creating 3 columns. I need 3 columns. 1 column for the probabilities with class 0, 1 column for the probabilities with class 1, and 1 column with the y predict values. So the first column name is probabilities with class 0. Here I am passing y pred prob, and this 0 means the first column of y pred prob. Here is y pred prob. You can see here is y pred prob. I want all the rows, but I need the first column for class 0 and I need the second column. Since index in Python start from the 0, therefore for first column I need to pass 0. For the second column I need to pass 1. So in this way I have put both the columns in my table. These columns are from ypred.prob And the third column is the predicted label. The name of the column is the predicted label, and I am getting the values of Y prediction, that is these values. So let's run this cell and observe the probabilities. Now we can see that from 0 to 39, we have 40 sample, and this is very informative table. This table is giving us the probability with class 0, probability with class 1, and we can see that since the probability with class 1 is high for the first sample, so the predicted class is 1. So we can see that all these probabilities values are right, and we are getting the predicted class according to the highest probability with respect to class. Here the highest probability is with class 0, so the predicted class is also a 0. Here we can also see that for this sample whose index is 9, so this is our 10th sample, the probability with class 0 is high, so the predicted class is also a class 0. So in this way, using pandas, we have created a table, and we can see that this function is returning a correct values of a probability and the correct value of the predicted class. Now the model has been trained and model has been testing. Now it's time to calculate accuracy. First, we will calculate the accuracy manually to get the understanding. So here I am creating predictions again, and these are my original test labels. So it depends upon how many test labels are exactly predicted by the model that will count the accuracy value. So these are the actual test labels, and these are the label predicted by the model. If all the predictions are correct, that is all Y pred is equals to Y test. So in this case, what will happen? Our accuracy will be 100%. Let's see how many of them correct. So we can see that there are few false values as well. So how many of them correct? We have to take the sum of those values of predicted which are equal to the original test value. So let's run this cell. So we can see that out of these 40 value, because we know that our test samples has 40 samples, our test data has 40 samples. Out of these 40, 32 samples were classified correctly. So if I want to calculate the accuracy, I have to divide this 32 by 40. So here is the sum 32, which is here. And here I am dividing with the total length of my testing data. So I should get 32 by 40. So 32 by 40 is 0.8. So this is the way of calculating the accuracy manually using Y pred and Y test. The other way is that you have Y pred and Y test. You can equal them and take the mean which is present in NumPy. And also you can see the accuracy which is equals to 80%. So here I have multiplied the accuracy with 100. That's why I am getting the accuracy into 80%. So 0.8 and 80% are equal. Here is the representation in percentage. So this is also the way of calculating the mean. That is, first you are taking the sum, and then you are dividing with the total number of samples. So you can now do it directly using NP-mean. Now it's time to create the confusion matrix. We have already calculated the accuracy. Now it's time to create the confusion matrix. So how we will create the confusion matrix? So from sklearn.matrix, we will import confusion matrix function. So in this function, we will pass Y test, that is our original testing labels, and Y pred, our predicted labels. And if I run this cell, I will get the confusion matrix. Now in the confusion matrix, we have 14, 5, 3, and 18. So we should remember from our theory lecture on confusion matrix that this 14, the first element is a true negative. The second element, this 5, is false positive. Then we have false negative. And this 18 is basically a true positive. So we should remember that if we have a 2 by 2 confusion matrix, the name of element should be remembered, that which is true negative, false positive, false negative, and a true positive. Now there is another method of generating a confusion matrix. So here from sklearn, I am importing confusion matrix. Now I am also importing F1 score, precision score, recall score, accuracy score, and confusion matrix display. So here I will calculate the confusion matrix, precision, recall, F1, and I will also plot the confusion matrix, and I will display in the form of figure. So look at this. So I have to run this cell to import all these functions. Now look at this code. Here I am creating the confusion matrix. So the input parameters are always Y test and Y pred. Here I want to display confusion matrix. So I have to pass confusion matrix is equals to CM, which is the confusion matrix. And I want to display my labels, which are 0 and 1. Here display.plot x ticks rotation is equals to 45. On the horizontal axis of the confusion matrix, the labels will be rotated by angle 45 degree. We will see here I am getting the information from the figure, so that I am adjusting the width of the figure equals to 8, and I am also setting the height of the figure equals to 8. So here I am getting the information by get figure function, and then I am setting the width and the height of the confusion matrix which I want to display, and here I am showing this. So let's run this cell and to see the confusion matrix. So we can see that we have values 14, 5, 3, and 8. Now if I want to increase the size of these font especially, so this is the size of the confusion matrix which is adjusted by these two 8. But if I want to increase the size of the font, in that case I am using this here font. So font, the weight of the font is bold. I want a font to be bold. I want the font size to be 15, and here I am passing font is equals to font, and this is my RC parameter in PLT, and we have learned about these RC parameter in our section on Python crash course. So if I run this cell, and now if I run this cell, I can see these values are bold and their size is also better. So here we can see that the predicted label along the x-axis are at the rotation of 45 degree, because we have passed the x-axis rotation equals to 45 in our line of code. Now we can confirm that this is 14, 5, 3, and 18. So this was another way of creating the confusion matrix just in the form of matrix, and here I am displaying in the form of figure. So the values are 14, 5, 3, and 18. So we can see that the values are 14, 5, 3, and 18. So this is the same confusion matrix, but this is another way of generating the confusion matrix. Now I need to calculate accuracy, precision, recall, and F1 score. So I have already imported these values. If you can see, I have imported F1 score, precision, recall, and accuracy score. Now I can use this function. So accuracy score, I am calculating the accuracy score. So I need to pass y test and y pred. Normalize is equals to true, that I am not going to calculate the accuracy in percentage. Therefore, normalize is equals to 2. Dot round 3 means I need only 3 places of value after the decimal. Therefore, round is equals to 3. For precision, I am using the function precision score. I am again passing y test and y pred. Here, average is equals to macro. Macro means that this precision value will be the precision value of both the labels. It will be the average of the precision. This precision value will not give me the precision of class 0 or the precision of class 1 or a label 0 or a label 1, but this will be the average of the precision of all the labels. That's why I am passing average is equals to macro. And for precision, I also want to get the values up to 3 places of decimal. The same is for recall score, that I have to pass y test and y pred, and average is macro. And for F1 score, I have to pass again y test and y pred, and the average is macro. So if I run this cell, I will be able to calculate accuracy, precision, recall, and F1 score. And here I am printing this. So this print will create space. This print space will create space after printing the value of accuracy. Let's run this cell and see all these 4 metrics. So we can see that our accuracy is 0.8, our precision is 0.803, our recall is 0.797, and our F1 score is 0.798. So in this way, we have calculated all the values. So what these values are telling us? These values are telling us that our data set is a unbiased data set. It has equal number of labels for both class 0 and class 1. Therefore, its accuracy and precision and recall and F1 are approximately same. So we have an unbiased and clean data. Therefore, we are getting all these 4 metrics with high values. Now, another way of observing these values is to print the classification report. So for printing the classification report, I am importing classification report from sklearn.metrics. I am importing classification report. Let's run this cell. And here I am printing the classification report. So my inputs are always y test and y pred. Let's run this cell and we can see that this is our classification report. So this is the precision value. If you see, this is the precision of class 0. This is the precision of class 1, and this is average precision. So here we get the average precision because we pass average is equals to macro. But in classification report, we can get the precision, recall, and F1 score of every label. So these two are our labels 0 and 1. So these are the average values. Average precision, average recall, and average F1 score. And here is our accuracy. So these are support. And because when we split the data, so 19 out of 40 samples in a testing data belongs to class 0. And when we split the data, so the 21 samples belongs to class 1. So we have total 40 samples. So accuracy is calculated using all 40 samples. Similarly, the precision is also calculated with all 40 samples. Recall is also calculated, and F1 score is also calculated with all 40 samples. So we have total 40 samples in all, because initially we had 200 sample and we split the data into 80-20 ratio, where 20% was the testing sample and 20% of 200 was 40. So this support indicates the number of total sample which we use to calculate these value. So we have 19 samples, test sample for 0 class, and 21 test sample for class 1. Now it's time to plot the ROC curve. So I will import ROC curve display from sklearn.matrix. Here I am setting the figure size of 12/8, and I am basically creating a subplot. I need one row and one column. One row and one column mean I just need one location, because there is one ROC curve for this whole data. So the function is ROC curve display dot from predictions. So we are calculating from the prediction. So I am passing the first input parameter is y test, then y-pred drop intermediate is equals to false. So it means I am not going to drop any of the samples. I want my ROC curve to include all the samples. Here axis is equals to x. Here I have defined the axis where I will plot this ROC curve. So axis is equals to axis, line width is equals to 3, and color is magenta. Let's run this cell and see ROC curve. So this is our ROC curve, and we know from our theory lecture that ROC curve is the curve between false positive and true positive. So here we can see that it is the curve between a false positive and a true positive. And inside or under this curve, area under the curve, AUC is standing for area under the curve. And you can see that area under the curve is 0.8 or 80%. So this area under the curve basically representing our precision value, which is also 0.8. So we know from the theory that precision depends upon all the positive labels, because it has the equation in the numerator. It has a true positive divided by true positive plus false positive. So precision is only looking for the positive labels, whether they are true or false. So that's why if we plot a curve between a false positive and a true positive, the value which we are getting is the precision. So this is our ROC curve, and area under the ROC curve is 0.8, which is representative of the precision of the model. So in this project, we learn how to train and test our logistic regression model. The most important thing which we learn in this project is how to evaluate the model by calculating confusion matrix, precision, recall, F1 score, and the accuracy. And finally, we learn how to plot ROC curve. So I hope you understood everything of this project. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will solve project 3 on logistic regression. So what we are going to learn in project 3. So basically in project 3, we evaluate the performance of logistic regression model based on cross validation. So here I am in my Google Drive. This is my course material folder. Click on this. Then here we have 3 sections: introduction, supervised machine learning, and unsupervised machine learning. Click on supervised machine learning. Inside supervised machine learning, I have a logistic regression folder. Inside a logistic regression folder, I have project 3 logistic regression _CV, where CV stands for cross validation. So if I click on this file, it will be open in Google Colab. So let's click on this file so that we can open it in our Google Colab environment. So here I am in my project 3. So for project 3, I need to import a lot of libraries and function. First, I need NumPy. Then I will import a function make _ classification from sklearn.datasets. Then I will import k-fold, because I need k-fold validation. So I'm importing k-fold function from sklearn.model _ selection. So from these sklearn.model _ selection, I am also importing cross-val score and cross-val predict. From sklearn.linear model, I am importing logistic regression. From sklearn.model underscore selection, I am importing train test split. From sklearn.metrics, now here I am importing a lot of evaluation metrics, that is confusion metrics, F1 score, precision, recall, accuracy, and confusion metrics display, where we will display our confusion metrics in the form of figure. Then I will need a classification report, which I am printing, or I am importing from sklearn.metrics, and later on I will use this function to print my classification report. I need matplotlib and I need pandas. So let's run this cell to import all these necessary Python libraries. So if you remember in our project 2, especially in the part 2 of our project 1, especially in the project 1, part 2 of the project 1, and also in project 2, we create data using a function make underscore classification. So here we are again going to use this function make underscore classification. The number of samples I am passing is 2000. The number of features this time is 20. So I am creating a big data with 20 features and 2000 samples. Out of 20, I have made 19 features informative and 1 feature redundant. So number of classes, I am getting 2 from this data set, and random state is equals to 42. We learn that this random state ensure that every time I run this cell, I will get the same data sample both in labels and features. So let's run this cell to create the data. And here we have seen the shape of my feature. It is 2000 by 20. That is, our feature matrix has 2000 sample and 20 feature, which is according to these values, which we passed as an input to our function make underscore classification. We also want to check our unique labels. So the function is np.unique. Let's click on it. So we can see that we have 0 and 1. We have 2 unique labels, 0 and 1, because we have passes number of class is equals to 2. Now it's time to standardize the train data. So basically this data set, we are going to train our logistic regression model. So this is our training data. So we want to standardize the data. So we have to import standard scalar from sklearn.preprocessing. Here I am instantiating standard scalar and I am calling it SC. And here I am using sc.fit underscore transform. So we have learned that whenever we have to standardize the train data, we have to use fit underscore transform. The fit is for the training and transform means this fit transform will transform this our X or our feature into the standard scalar form, or basically it will standardize our training component of the data. Let's run this cell and we call it X again. Now we have to train the logistic regression model. We have training data X and we have Y. So it's time to train our model. So here I am instantiating logistic regression function. So this will give me the model. And here I am fitting my logistic regression model to my training data. So the features in my training data are X and the label in my training data are Y. So if I run this cell, I will get the train model. Now this LR is train model. Now student, you have seen that I did not do any train test split here. I can do it, but in order to see the performance on a totally unseen data, so I am using this data set as a training, and now my model has been trained on this data. Now it's time to test the model. So in order to test the model, now I am generating a totally unseen test data. I am again using make classification function here. This time I am using number of samples is equals to 400. Number of features is equals to 20. And I have only 19 features are informative. 1 feature is redundant. Number of class is equals to 2 and random state is equals to 42. So here I am generating a test data which I will use for testing the model. Let's run this cell to generate the test data. Now it's time to standardize the test data before passing it to the model. So here I am using the same standard scalar SC, but this time for the test data, therefore I am using sc.transform x data. So we have to be careful when we standardize the test data. We cannot pass fit underscore transform. Fit underscore transform is only for the training component, but for the testing component, whenever we standardize the test data, we need to write sc.transform. So now the testing data has been standardized. Now it's time to get the prediction from the test data. So we have our model LR. So in order to get the prediction from the model LR.predict, and here I am passing my test data. Here I have my Y predictions. Now it's time to calculate the accuracy of the model. Now, accuracy is basically depends upon how many predicted labels are equal to the testing label. So here I am getting ypred is equals to ytest. Here I am summing the values of those labels which are equal. And here I am taking the mean by dividing with the total samples. So we use this equation in our project 2 as well. This is the manual way of calculating the accuracy. Let's run this cell. And if we want to see the accuracy, it will be, we have to type it. And if I run this cell, I will get the accuracy of 52.25% or 0.5225. If I want to express this in form of percent, so I have to multiply the accuracy by 100. So here I am again using the same approach, that is summing, and by dividing the total length, that is taking the mean. So by doing this and by doing this, I will get the same accuracy. So this time, rather than doing it totally manually, I am using np.mean function. So let's run this cell and I get the accuracy in percentage, which is 52.25. Now it's time to create the confusion matrix. And here I am setting the font size and the weight of the font. Let's run this cell and create the confusion matrix. So student, the code for the confusion matrix, which you are observing here, which you are looking here, is exactly the same which we used in project 2. So it is highly recommended that do not skip any project before this project, because in order to understand project 3, it is important to learn project 2 as well. So these lines of code are exactly present in project 2, where I explain them in detail. So here is my confusion matrix. And now in confusion matrix, we have a large number of samples, because if we see in the testing, we have 400 samples. So if we add them, we will get the value 400. So this is our true negative and this is our true positive. So here we have false positive and false negative. So we can see that we have a large value of false positive, which is type 1 error, and false negative, which is type 2 error. So that's why its accuracy is very less, that is only around 52%, because there is a large number of misclassified labels here. So we have completed the evaluation of a model on our training data and a testing data. Now we can also calculate the value of accuracy, precision, recall, and F1 score. Now student, these lines of code are exactly the same which you saw in project 2, where I explained how we have calculated the accuracy, precision, recall, and F1 score, and what is the meaning of this macro. So let's run this cell to print the value of accuracy, precision, recall, and F1 score. And we can also print our classification report. So we can see that this is the precision of class 0. This is the precision of class 1. And this is the average precision. If I add them and divide by 2, I will get this value. So this support will tell us how many testing samples we use in order to calculate this average value. So we use 400 testing samples for accuracy, for recall, for precision, and for F1. So out of these 400, 200 belongs to class 0 and 200 belongs to class 1. So this is complete classification report in terms of precision, recall, accuracy, F1 score, and in terms of total number of testing samples. Now we can also plot the ROC curve. So I will import ROC curve from sklearn.metrics. Again, student, in project 2, we have seen this code. I explained you this code there, that how to get ROC curve display from sklearn.metrics. So the inputs are ytest, ypred, drop intermediate is equals to false mean. We are not going to drop any testing sample. We want every sample in our ROC curve. The line width is 3 and color is magenta. So let's import this. Let's run this. So we can see this straight line, and this straight line has only precision of 52%. We learn that area under this straight line. So okay, let me reduce the size so that we can see it clearly. So if I reduce it to 10 by 7, then what will happen? So if I reduce it to 10 by 7, then we can see it more easily. So we have false positive on x-axis, we have true positive on y-axis. So this ROC curve is the curve between false positive and true positive, and the area under the curve. So this is the curve. So this area represent the area under the curve. So the area under the curve is 0.52, which is the representation of the precision value of the model. So till now, we have done everything with respect to logistic regression model. We train the model, we test the model, and we evaluate the model. Now it's time to do this evaluation again with the help of cross validation, and then compare the result when we do evaluation without cross validation. So I am using now cross validation strategy to for logistic regression in order to get the performance. So I am using 5-fold. So I want to split my data into 5 components. So here the random state is 42 and shuffle is equals to true. So the shuffle true means that after every split, our data should be shuffled before the other split. So here I am creating again my logistic regression. This time the name is model underscore CV, that is cross validated model. Here I am calculating the scores. So I am getting the value of accuracy here. The input are model, my training component, and my predicted values. So let's run this cell to get the average value of the score after 5-fold validation. So we can see that our accuracy on the training is 0.83. So we can see that our accuracy on the training data is 83%. Now it's time to get the performance of this cross-validated model on a testing data. So we have a testing data. We know we have separately generating this testing data. So the input is model X test, the testing component, the testing label, and cross validation, which is equals to 5 here, or we calculate this value from this line of code. Now I need a function cross underscore val predict in order to get the prediction from a model. And I am calling it ypred underscore CV. That is, this is the prediction of a model using cross validation. So let's run this cell. And here I am printing the accuracy. Now, student, you can see the accuracy is 77.75 on the testing data with cross validation. If I compare it without cross validation, so without cross validation, this accuracy was 52.25. So we can see that with cross validation, the logistic regression has performed so well that its accuracy has increased up to 25%. Now it's time to display the confusion matrix. So we can see that the amount of false positive samples and amount of false negative sample has been reduced. It is 42 and 47 now. Previously, it was 77 and 114. Previously, the true values were 123 and 86. Now they are 158 and 153. So we can see that our model has improved a lot when it is trained on cross-validation basis. Now it's time to print the classification report. Here we can print the accuracy, precision, and recall. So the accuracy is 77.8, precision, recall, and F1. All the scores are almost same. Here we can print our classification report. So we have 400 test samples. So we have calculated accuracy, precision, recall in the same way as we calculated without cross-validation. So all these are the repetition of a code. Only difference is here we tested our model based on the cross-validation, and we get the improved value of the accuracy. And here our predictions are called ypred underscore CV. So we are passing ypred underscore CV everywhere. So this is Y test, and here we are passing ypred underscore CV everywhere to calculate accuracy, precision, recall, and F1 score. Now the final step is to plot ROC curve. So we can see that this is a better ROC curve. It is a far more better ROC curve than the previous. If you see the previous curve, it is only representing or giving a 52% precision. It has high false positive rate. Now the false positive rate has been reduced. We can see that the false positive rate has been reduced and it has effect on our ROC curve. Now the area under the ROC curve is very high as compared to the previous value of logistic regression where we did not use cross validation. Now we can see that the area under the curve is 78%, and this area under the curve which is 0.78 or 78% represent the precision value of the model. So in this project, we learn how to improve the performance of logistic regression model with cross validation. We see by using cross validation, we get less type 1 error and type 2 error. That is, the value of type 1 and type 2 error has been reduced. You can see these are the reduced value, and it has impact on our ROC curve as well. So I hope you understood this project 3 very well, which was on the performance of logistic regression model using cross validation. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will solve our project 4 on logistic regression. So basically in this project, we will apply logistic regression model on a multi-class dataset. That is a dataset having more than 2 classes or 2 labels. So here I am in my Google Drive, and here is my course material folder. So click on this. So I will get 3 major sections. There are 3 folders: introduction, supervised machine learning, and unsupervised machine learning. Inside the supervised machine learning, I have a folder logistic regression. Click on this. So inside logistic regression, I have my project 4, which is about the multi-class classification using logistic regression. So click on this folder so that we can open it easily in our Google Colab environment. So here we have our project 4 in Google Colab. So in project 4, I need NumPy, I need logistic regression. I will import it from sklearn.linear_model. I will also import a function train_test_split from sklearn.model_selection. I will import matplotlib. I will also import pandas. I need a panda here. I need display. So I will import display from IPython, and I will also import Seaborn as a SNS. So these are the important libraries which I need for this project. Let's run this cell to import all these necessary libraries. Now here I am getting a data set from a Seaborn. I have already import Seaborn as SNS. So there is a data set named as Iris. So that data set is present in Seaborn. So here I will load dataset from Seaborn. So the command is SNS. SNS is the name of a Seaborn library. So I have imported Seaborn library with the name SNS. SNS dot, the function is load_dataset. And here I am importing a dataset known as Iris dataset. And after importing, I am saving this dataset into a variable known as Iris. So this dataset is basically a flower dataset. This dataset contains 3 different flowers, and we also have the feature of the flowers. So basically we have to classify 3 different flowers in this project. That's why it is a multi-class project. That is, we have more than 2 classes. Let's run this cell and load this dataset, as well as we want to see the shape of the dataset. So if I run this cell, I get the shape 150 by 5. So I have 150 sample. So what actually is happening, I have 3 different kinds of flower. So I have 50 samples for each flower. Next is that I have 5 columns. So out of 5 columns, the 4 columns belongs to the feature, and 5th column belongs to the class or label of the dataset. Here I can see the top 5 samples of a dataset. If I want to see, so these are the top 5 samples out of these 50. So the feature are sepal length, sepal width, petal length, petal width, and these are the species. Here, since I have selected only 5 samples, therefore that is, I am observing the head of the dataset. Therefore, I can only see the first species or first label, which is setosa. So if I can expand it to like 100 features, or I just want to see the complete data set. So we can see that I have 150 samples. We have a setosa, we have a virginica, and between them we have another versicolor, the 3rd kind of a flower. Now it's time to see the species. So species are present here. So if I want to see the species and the 3 different labels, which I said about this dataset, that this is a dataset of a flowers with 3 different kind of flower. So here are the 3 different labels. So the labels are setosa, versicolor, and virginica. Since these three are the flowers, so every flower has a sepal length, sepal width, petal length, and petal width. So this is the explanation of the iris dataset. So iris dataset is a dataset of flowers having 4 features, and in this dataset we have 3 kinds of flower named as setosa, versicolor, and virginica. Now it's time to see these flower. We can display these flower. So first I am going to show you the iris setosa, that is the setosa class of this dataset. So I am getting this from this site. So I am using from ipython.display. I am importing the image, and I want to show you the image of this setosa class of a iris dataset, which I am getting from this website. Let's run this cell and observe. So this is the image of setosa flower. Similarly, I can see versicolor flower. If I run this cell from the same website, I can get the versicolor, and similarly I can get the virginica label of the flower, that is the third kind of flower. So we can see that we have 3 different kind of flowers. Their petals are of different length and shape. That's why we have the features sepal length, sepal width, petal length, and petal width. So till now, what we have done in this project is that we have loaded a data set from Seaborn. This is an iris data set. This iris data set is about 3 flowers. So the name of the flowers are setosa, versicolor, and virginica, and we will use these names as a label in our data set. So these are the images of these flowers, setosa, versicolor, and virginica. Now the problem is we have to transform these labels into integers. So the names are setosa, versicolor, and virginica. So we cannot give these names directly to our computer or our machine. We need to transform them into the integer. So look at how I am transforming these labels into the integer. So I am getting iris.species.replace. So the iris.species is the species is the column where these labels are present. If we go back, we can confirm species is the column and iris is the name of the data set. So in order to get these, I need iris.species, and I am using a function .replace. So what to replace? So replace setosa with value equals to 0, and I want to replace it permanently. Therefore, in place is equals to true. Second, I am replacing versicolor with the value 1 and virginica with the value 2. So after this transforming, the name of my labels will be 0, 1, 2, where 0 will indicate setosa, 1 versicolor, and 2 virginica. Let's run this cell. And now if I want to see the head of my data, I can see that instead of setosa, the 0 is written in the labels. Now here iris.species.value counts. If I want to see now, I have 50 samples belongs to class 0. I have 50 sample belongs to class 1, and I have 50 samples belongs to class 2. Now these are the species. Previously the name was setosa, versicolor, and virginica. Now the name of the labels are 0, 1, and 2, and they are present in the column name species in our dataset. So here by using the function .value counts, we are able to find the number of samples belongs to the particular class. Now it's time to extract the features. Extracting features means I need all these columns except one, except the last column, that is the species. So in that case, I am using iris.integerLog. I need all the rows, I need all the columns except the last. We know that the last column index is -1. So here I am extracting the features which are present in all the columns other than the last column. So let's run this cell to extract the features. And here I am extracting the labels which are present only in the last column. So I am extracting all the rows of the last column, and these are called the label of the dataset. So I have extracted features and label. Now it's time to perform a train test split. So for train test split, I am using 20% data as a testing. Therefore, 80% data will be used as a training. So I am passing X and Y values to my train test split. So these are the feature, these are the label. So the test size is 0.2 and the random state is equals to 42. Now let's run the cell to get the train and test split. So the output has 4 values. After performing this function, I will get the training component of the data, the testing component, the training labels, and the testing label. So here, if I want to see the shape of my testing component, so we can see that its shape is 30. The reason is that we have total 150 samples. Out of these 150 samples, we are using 20% as a testing and rest 80%. So our test samples are 30 and every sample has 4 features. So we can see that we have 4 features: sepal length, sepal width, petal length, and petal width. So the size of our testing data after the splitting is 30 by 4. We have 30 sample and 4 feature. Now it's time to standardize both the training and testing part. So for this, we have to import standard scalar, which is present in sklearn.preprocessing. So I will import standard scalar. Here I am instantiating standard scalar and I am assigning the variable sc to it. And now it's time to apply these standardization both to the training and testing component of the data. So we have to be careful. We study in the previous projects that whenever we have to standardize our training component, we have to use fit_transform. Fit function can only be used for the training component. It cannot be used for the testing. So for training, we will use fit_transform, and for testing, we will just transform this into the standard scalar sc.transform. Let's run this cell and we get the standardized data. Now it's time to applying logistic regression. Here I am instantiating logistic regression and I am calling it as a model. Here I am fitting my model to the training component of the data, that is X train and Y train. So basically with this line of code, I am training my model with the training data, and that trained model is called LR. So LR is my trained logistic regression model. Now the next important step is to get the probabilities of classes about the test data. So we have now seen this function many times, which help us to find the probabilities of the classes. So the function is LR. LR is our model. So the function is .predict_prob A. It is giving us the probability of a testing sample with respect to each class. Let's run this cell to see the probabilities. Now there is a change. Previously, whenever we transform our classes into the probabilities, we have 2 columns. Now we have 3 columns in these probabilities because we have 3 class. Class 0, which is Setosa, class 1, which is versicolor, and class 3, class which is Virginica. So we have 3 classes, but they are represented by 0, 1, and 2 because index in Python start from 0. So this is our 0 class, this is our first class, and this is our second class. So we have total 3 classes, but they are numbered as 0, 1, and 2. So if we see here, the probability with class 1 is high. If we see the sample 1, it has 3 probabilities. So it has the high probability with class 1. It means our first test sample belongs to class 1. Similarly, if we see our 40th sample, it has the high probability with class 0. So it belongs to class 0 of the data. Let's get the class prediction. So for class prediction, we are using lr.predict. So here we can see that our last sample belongs to class 0 and our first sample belongs to class 1 because it has high probability with class 1. So in this way, we have calculated the probability for the test samples for each class. Now we have also calculated the class predicted, that is the prediction class. Now it's time to create a table where we can see all these probability values and predicted class. So in the previous projects, we know how to create that table. Now this table will have 4 columns because we have 3 classes. So we will have the first column, we will have probability of class 0. For second column, we will have probability of class 1. For the third column, we will have probability of class 3. So for these 3 columns, we will get these 3 values. So this will be the value of the first column in the table. This column will be the value of a second column, and this column will be the value of a third column in the table. And the fourth column has a name predicted class, and this column will get these values. So let's run this cell to see the table clearly. So we can see that our first column represents the probability of first sample with class 0, then with class 1, and the third column represents its probability with class 2, and here is the prediction. So we can confirm that this sample has highest probability with class 1. Since it has a highest probability with class 1, so our model prediction is right. Model is predicting that this sample should belong to class 1. Similarly, we can go through for each of these 30 samples, and we can confirm here that if we see this sample, it has the highest probability of 0.98, that is 98% with class 2. Therefore, our model is assigning class 2 to this sample. So we have seen that our model is generating the correct value of the probabilities as well as the class. So we have formed this table. Now it's time to evaluate the model. Model has given us the values of probabilities, and model has given us the class predictions. Now it's time to evaluate. For evaluating, what I can do is I can calculate the accuracy. Now, how to calculate the accuracy here? So basically, accuracy is the mean value of y-pred is equals to y-test. So basically, we have to see how many y-pred is equals to y-test. If I run this cell, I can see all y-pred are equals to y-test. So this is a great performance of our logistic regression model. We can see that, and we are expecting that we are getting the 100% accuracy because there is no false value. All the predictions made by our model are equal to the true values. So if I calculate the accuracy here, I am getting the equal values, and here I am taking the mean. Means I am summing these values, and then I am dividing with the total number of samples. So if I run this cell, the accuracy will be 100%. So we can see that I have transformed the accuracy into percent by multiplying the accuracy equation by 100. So the accuracy is 100%, and we have confirmed from here that all the predictions made by model are exactly equal to the actual label of a testing component of the data. Now it's time to create a confusion matrix. Here we are setting the weights and font for the confusion matrix. Here I am importing the confusion matrix, F1 score, precision score, recall score, accuracy score, and confusion matrix display. All these function from sklearn.matrix. So we have seen in previous two projects that how to import this using sklearn.matrix. Let's run this cell to import. Here I am creating my confusion matrix. So we can see this is the shape of the confusion matrix with the accuracy of 100%. So if your data accuracy, or if the accuracy of your model on the testing component is 100%, so this will be the shape of your confusion matrix. So one more important thing to remember is now we have three labels, 0, 1, and 2. That's why the size of this confusion matrix is 3 by 3. So we can see that all the true values are present in the diagonal, and all these values are basically the error. So here there is no error. So we can see that if the accuracy of a model is 100%, its confusion matrix looks like this. So all the values are in the diagonal, and we know from the theory of the confusion matrix that the diagonal of confusion matrix returns the true values, that is a true classified sample, and other diagonal values are the errors, or they are the false classified value. So there is no false classification in this confusion matrix because the accuracy of our model is 100%. Now it's time to calculate accuracy, precision, recall, and F1 score. We have already imported this from sklearn. Here you can see that we have imported F1 score, precision, and recall score as well. So it's time to calculate accuracy, precision, recall, and F1 score. So here is the typo. I have to adjust it. This is not F, it should be AND. So now it is calculating accuracy, precision, recall, and F1 score. So we have seen these equations now many times before this project, that these equations are used to calculate accuracy, precision, recall, and F1 score. Now it's time to run this cell and see the values. So we can see that every value is 1. That is, accuracy is 100%, precision is 100%, recall is 100%, F1 score is 100%. So we have a clean data, and our model has performed so well on this data that its accuracy, precision, recall, and F1 all values are 100%. Now it's time to get the classification report. So I am importing classification report from sklearn.matrix, and here I am printing my classification report. So we can see that we have 30 testing sample, and we calculate the precision, recall, F1, and accuracy using all these 30. So we can see that the average value for the precision, recall, and F1 score is 1, and the value of the precision recall and F1 score for individual class is also 1. Now it's time to plot ROC curve. So we have import ROC curve display from sklearn.metrics. We have seen these lines of code previously in project 2 and project 3 as well. Let's run this cell to see the ROC curve. Now this ROC curve is very interesting. Now I can reduce the size so that I can clearly visualize this. Let's run this cell, and now we can clearly visualize this ROC curve. So we know from our previous projects and theory that ROC curve is the curve between the false positive rate and the true positive rate. And the area under the curve represent the precision of the model. Since in precision calculation, we use the false positive and true positive, therefore area under the ROC curve represent the precision of the model. So this AUC, that is area under the curve, is 1 or 100%. And we can see that there is no false positive value because model has classified every sample correctly. There is no wrong classification, whether it is false positive or false negative. But we do not need any negative label for ROC. So we can see that this has a 0 value, and we can see this true positive has a 1 value, that is 100%. So all the labels are correctly classified. Therefore, the area under the curve here is 100%. That is the precision of our model is 100%. So in this project, we learn how to implement logistic regression for a multi-class problem. We select the iris dataset, which has 3 classes, that is the Setosa, Versicolor, and Virginica, and we apply logistic regression model. So our logistic regression model has performed well, and we get the value of accuracy equals to 1, that is 100%, and same values for precision, recall, and F1 score. And we also see the important thing here that if our classes are 3, then the size of confusion matrix is also 3, and the true values are present only along the diagonal of the confusion matrix, and rest values are the error or the misclassification. So we see when the accuracy is 100%, there is no error values and all the classes are classified correctly. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will solve our project 5 on logistic regression. And for this project, we are going to select a challenging dataset. That is, this dataset will be more challenging than the previous projects. So I am here in my logistic regression folder, and I have here my project 5. If I click on this file, it will be open in Google Colab environment. So click on this file, and here I am in my project 5. So for my project 5, I need to import all these necessary Python libraries. That is, I need logistic regression, I need train test split, I need NumPy, Matplotlib, and I need pandas. So let's run this cell in order to import all the necessary libraries. So for this project, I am going to use the dataset known as Titanic_train.csv. So this data is present inside my logistic regression folder. So this is my logistic regression folder, and here is the dataset. We know that in order to read the dataset from the particular folder, we need to mount the drive and we need to set the path. So in order to save the time, we have already mounted the drive here and we have already set the path. Now you know how to mount the drive and how to set the path. We have done this now many times in this section and in the previous section of the course. Now it's time to import the data. Let's run this cell. So data have been imported and we can see the shape of the data. It has 891 samples and 12 columns. Let's see the head of the data, that is the first 5 sample of the data. So we can see that this data set has quite a few number of features. We have passenger ID, survived. Now survived, this column we will not use as a feature and we will use is as a label. And it has 2 unique values, that is 0 and 1. If the passenger survived, we will assign a label 1. And if it is died, the label will be 0 for that passenger. This is passenger class, name of the passenger, sex, age, and there are 2 more features. Let's see what does these features mean. We have a ticket number, we have fare, we have a cabin, and we have embarked. So the last column is embarked. So embarked implies where the traveler mounted from. So there are three possible values for embarked: Southampton, Cherbourg, and Queenstown. So these were the three places from where the traveler mounted. So we will find that this column will have three values. Similarly, a sex is also a categorical column. So this embarked is the categorical column. Sex is also a categorical column. It has two values, male and female. Now these two columns, SIB, SB, and PARS. So basically, if we see SIB, SB is the number of siblings or spouse of a person on board, and PARS is the feature contained the number of parents or children each passenger was touring with. So basically, these two features represent the number of family members traveling with the passenger. Now, this is a challenging dataset because it has a feature in the form of integers like the passenger class. We have features in the form of categories like sex and embarked, and we have features in the form of float like fare. So in this way, we have every kind of features. Now, first step should be to check the number of passengers died and number of passengers which are survived. So we have to use the information of this column, which is the survived. So the name of our data is train. So what we are going to do is to extract the value count information from this column survived. Let's run this cell and we can see that there are 549 passengers who died in the Titanic accident and there are 342 passengers who survived. So we can see that about 60% of the passenger died. Now it's time to drop the irrelevant feature. So if we go back to the passenger ID, the name of the passenger, similarly the ticket and the cabin. So these are the irrelevant features because they have they are not influencing our survived, which is our label. So they are the irrelevant features. They have no effect or influence on our target variables. So in that case, we can easily remove them by running a command train.drop, and here we are passing the name of the columns. Since these are column, therefore axis is equals to 1 and in place is equals to true means we are removing them permanently. Let's run this cell to remove them permanently. Now we are going to check the null values of our data set. Let's run this cell. So we have train dot is null any. So we can see that we have null values in the age column and we have null values in the embarked column. Now age column is a column where we have the values in terms of float. So how to deal with the null values which are present in the age? So basically what we will do, we will calculate the mean value of the column age and we will replace the null value in this column with the mean value. So how to do this? So we will use train.fillna. Train.fillna means fill the null values. So how to fill the value? We will calculate the mean of the age column and then we will replace the null value of the age column with that mean value, and then we will write in place is equals to true. In place is equals to true means that we are going to change it permanently. So let's run this cell and now check the null values again. So if we see that there are no null values in the age column now. Now it's time to deal with the null value in the embarked column. Now for embarked column, what is our strategy? That we are going to drop those samples which have the null values. So we are going to use train dot drop null values NA, that is drop null values in place is equals to true, that we want to drop these values permanently. So let's run this cell and now check the null values again. So we can see that there are no more null values in any of the column. And now we can check our data set again. So we can see that this is the data set without the null values. So in the first step of the data cleaning, what we have done is that we have removed the null values and we have dropped the irrelevant feature. After removing the null values and after dropping the irrelevant features, now we are left with those number of features, that is the passenger class, sex, age, SIP SB, this is part, then fare and embarked. So this first column survived will be our label. So I stop this lecture here. In the next lecture, I will continue this project. See you there. Hi everyone, welcome to this lecture. So this lecture is a part 2 of our project 5. Now it's time to deal with the categorical data. Now we have two categorical features, that is sex and embarked. And we know that in order to deal with the categorical features, we need to create the dummy variables. Now it's time to create the dummy variable for sex and embark. First, we will create the dummy variable for our column sex. So we know that from pandas libraries, we can use get dummies function in order to create the dummy variables. So let's run this cell and let's see those dummy variables. So we can see that we have two variables, that is male and female, in our sex feature. And we can see that in the first sample, the value assigned to the male is 1. The reason is that our first passenger is a male. So therefore, there is a value 1 for the male in the first sample. If we see the second sample, our passenger is female, and we can see that a 1 value is assigned to the female, and this time the value assigned to the male is 0. It means this 1 and 0 depends upon the passenger. That is, if the passenger is male, the value will be 1, otherwise it will be 0. So we have observed that we do not need both the columns, that is female and male. If we drop our first column, we will be okay. If we use only male column as our dummy variable, it will be okay, because when a value 1 will be assigned to the male, it means that in that sample, the passenger will be a male. And if value 0 is assigned to the male, it means in that sample, the passenger is female. So therefore, we will drop our first feature or the first dummy variable. So the command is that pd.get dummy train x and drop first is equals to true. So let's run this cell and we can see that now we have only one category, that is male. Similarly, we can do this for the embarked as well. So when we create the dummy variables, now we can see that we have so many dummy variables C, Q, and S. The problem with those dummy variables is all the values in those columns are 0 and 1. So it seems that they are repeated value, they are dependent on each other, they are multicollinear. So in order to avoid the multicollinearity, we always drop the first feature. So here we are again dropping the first feature. After dropping the first feature, now we have the embark and sex in the form of dummy variables. Let's add those dummy variable to our original data. So our original data is train, and we have created two dummy variables for sex and embark. Now we will use pd.concat in order to add those dummy variable to our original data. And since we are adding in the form of column, therefore axis is equals to true. So let's run this cell and see our data now. So we can see that we have male, we have Q, and we have S. These are the dummy variables which we have added into our original data. Now, since the dummy variables for sex and embarked column, that is for this column sex and this column embarked, has already been created, therefore we need to drop those columns. So here I am dropping sex and embarked column. X is equals to 1 means I am dropping along the column, and in place is equals to true means I want to drop them permanently. Now we can see that all the columns for which we have created the dummy variables have been dropped, that is sex and embarked. Now we are left with data set which is in the form of our requirement, that is there is no categorical feature, there is no irrelevant feature, and there is no missing value. So that data set was challenging initially because there were the missing values, there were the null values, there were the irrelevant features, and there were the categorical features. So we have addressed all those issues. Now, after addressing all those issues, we still have a repeated value or the redundant feature. We can see that in this column, we have 3, 1. Here we have a lot of ones as well. Here we have already a lot of ones and zeros. So they are somehow repeated features in that sense that they are dependent features and they are some sort of multicollinear features. Okay, now the data set has been cleaned, the data pre-processing has been done so far. Now it's time to extract features and labels. So for features, we do not need this survived column because we have decided that this is our labels. So we will drop this column when we want to extract the features. So we have extracted the features. Now for our labels, we need this column survived. Here are our labels. Now it's time to perform a train test split. So for train test split, I am using 20% of a data as a testing and 80% data as a training. Now we have done the train test split. Now we can check the shape of our testing data. So 178 samples will be used in a testing data. Now it's time to perform another important data pre-processing step, which is the standardization of the data. So here I am importing a standard scalar from sklearn.preprocessing. Here I am instantiating the standard scalar and I am calling it SC. And here I am applying the standardization to my training component here and the testing component here. Let's run the cell to standardize the training and the testing component. So we have done all the data pre-processing. Now it's time to train our logistic regression model on this data. So I stop this lecture here and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this lecture is a part 3 of project 5. So in this lecture, we will train our logistic regression model. So the first step is to instantiate the logistic regression. So here we have instantiating the logistic regression and I am calling it as a model. Here I am fitting my model on the training component of the data. That is, I am training my model on the training data set. So let's run this cell to train our model. Now it's time to get the probabilities and prediction from the model by passing the testing component of the data. So let's run this cell. So we can see that these are the probabilities which are created by our logistic regression model. According to those probabilities, our first sample has high probability with class 0 and low probability with class 1. It means this first sample belongs to class 0. If we see the other sample, that is the second sample, it has the high probability with class 1. So this sample belongs to class 1. So these are the probabilities of each sample associated with the classes. So these are the probability predictions by our logistic regression model. Now it's time to get the class predictions. So in order to get the class prediction, we will use lr.predict and we will pass our testing component of the data to get the prediction of the classes. And here we are observing the probabilities, that is the class probabilities and class predictions in a single table. So this is the same line of code which we have used in project 4, in project 3, and in project 2, where we want to create the table of the class probabilities and the class predictions. So we have 3 columns. The first column is the probabilities of class 0, then probabilities of class 1, and then we have a predicted class. So we can see that for the first sample, the probability with class 0 is high. So our model is saying that it belongs to class 0. Similarly, for second sample, the probability with class 1 is high as compared to the probability with class 0. So our model is saying that this sample belongs to class 1. So in this way, we can see that the predictions of probabilities of our model is correct and they are accordance with the class predictions. Now it's time to calculate the accuracy. Here I am calculating the accuracy by comparing the predicted samples, the predictions with the original test labels. Let's run this cell to see the accuracy and we can see that the accuracy is 77.53. So the reason of this accuracy is that we have a challenging data set and we have so many features which are multicollinear. So we can see that we have the features which is passenger class, we have sibling features, we have parent and children feature, we have male, we have Queenstown, we have Southampton. So all these features have values 0s and 1 which are repeated values. That's why the performance of our model is not very high, that is it is less than 80%. Now it's time to create the confusion matrix. So we will import confusion matrix from sklearn.matrix, and here I am passing y-test and y-pred to this confusion matrix function. So this is my confusion matrix. Now we can display the confusion matrix in the form of image. So here I am setting the font, and here I am displaying this confusion matrix with the function confusion matrix display. But before this, I have to import this function from sklearn.matrix. So along this function, I am also importing F1 score, the precision score, recall score, and accuracy score. So let's run this cell to import, and let's run this cell to get the image of our confusion matrix. So we can see that this is the image of the confusion matrix. This value is a true negative, then we have true positive, then we have false positive, and we have false negative value. Now it's time to get the values for accuracy, precision, recall, and F1 score. So this is the same code which we used in project 2, 3, and 4 in order to calculate accuracy, precision, recall, and F1 score. Let's run this cell. And these are the values of accuracy, precision, recall, and F1 score. Now it's time to print the classification report. For printing the classification report, first we have to import the classification report from sklearn.matrix, and then we are going to print the classification report. Now we can see that in the classification report that we have 178 test samples in order to calculate the precision, recall, F1 score, and accuracy. Now out of these 178 sample, 109 samples belongs to class 0 and 69 samples belongs to class 1. So the precision of class 0 is high, it is 85%, and the precision of class 1 is low, which is 68%. And these are the average value. Similarly, the F1 score value with class 0 is high, it is 81%, and F1 score with class 1 is low, it is 73%. And this is the average value of F1 score. So we can see that our data set is not a balanced data set. It is unbalanced data set with more samples associated with class 0 and less samples associated with class 1. Okay, now it's time to plot ROC curve. Here we have the ROC curve, and we know that the ROC curve is between false positive and true positive. That's why area under the ROC curve always give us the value of the precision of the model. So here AUC represent area under the curve, and its value is 0.78, which is in accordance with the precision value. Now we can also calculate the base and weights of a bias and the weights of a logistic regression model as we calculated for our linear regression model. So if we write LR.intercept, we will get the bias of the model, and if we write LR.coff, we will get the weights of the model. Let's run this cell, and we can see that there are 8 weights total: 1, 2, 3, 4, 5, 6, 7, and 8. Why there are 8 weights? So definitely we will have 8 feature in our data set, and every feature has its associated weight. Let's go back and see the data set on which we apply our logistic regression. So that was our data set. We have this first feature. This is not our feature, these are the labels. So we have this first feature, passenger class, then age is the second feature, third, fourth, fifth, sixth, seventh, and eighth. So since we have 8 features, therefore we have 8 weights, that is each weight associated with the feature. So in this project, we learn how to deal with the challenging data. So challenging data is a data which has all kinds of features, that is categorical features, the features with integers value, and the floats value. Similarly, there are null values in the data set as well. So we have addressed all the issues with the challenging data set. First, we remove the irrelevant features from the data set. Then we deal with the null values. Then we deal with the categorical values. And finally, we apply our logistic regression model. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve our project 6 on logistic regression. So basically in this project 6, we will learn how to use grid search cross validation for logistic regression problem. So here I am inside the folder of logistic regression, and here is my project 6. So click on this file so that I can open it in my Google Colab environment. So here is my project 6. So in order to solve project 6, I need NumPy, I need make classification. So I will use this function in order to create the dataset. So I will import make underscore classification from sklearn.datasets. So I also need grid search cross validation function. So I will import it from sklearn.model underscore selection. Similarly, I need logistic regression, which I will import from sklearn.linear model. I need train test split, which is sklearn.model selection. I need matplotlib, and I need pandas. So let's run this cell in order to import all these necessary Python libraries. Now it's time to create a dataset. So I am going to use a function make underscore classification. I am going to pass number of samples is equals to 500. Number of features is equals to 2. and I need all the features to be informative. So number of informative features is also equals to 2. So there is no redundant feature. I need 2 classes or 2 labels, and random state is equals to 101. So I am passing random state because I want to generate the same sample every time I run this cell. So let's run this cell to create the data set and to see the shape of our X, that is our feature matrix. So the shape of our feature matrix is 500 by 2. That is, we have 500 samples and 2 features. Now see how many unique labels we will have in this data set. So we will pass a function np.unique, and here I am passing a label to this function, that is the value of y. So we can see that we have only 2 unique labels, 0 and 1, and the reason is that we have passed number of classes is equals to 2 during the data generation. Now it's time to perform a train test split. So I am using a function train test split. So my input parameters are feature, label, test size is equals to 0.2, and random state is equals to 42. So here I am using 20% of a data as a testing and remaining 80% data as a training. Let's run this cell to perform the train test split. So after train test split, I has 4 output. That is, I have the training component of the data, the testing component, the training labels, and the testing label. Let's see the shape of the training data. So training data has 400 samples and 2 features. So in total in the data set, we have 500 sample. And when we split the data into training and testing, since training is 80% of the total data, therefore the 80% of 500 is 400. Now it's time to apply grid search cross validation. Now student, till project 5, so this is our project 6. In all previous project 5 on logistic regression, we use the default values of the logistic regression function. That is, we did not pass any input parameter to the logistic regression function. But for grid search cross validation, we need to know what kind of input parameters we can pass to the logistic regression. And we will provide then all the possible combinations of those parameters to the model, so that model can select the best possible parameter from the given possible combinations of the parameter. So first of all, we need to know what parameters we can pass. So for this, we have to see the document of this logistic regression function. In order to see the document of logistic regression function, we have to use the help function. So we have to pass this logistic regression to this help function in order to see the document of the logistic regression and to see what kind of input parameters we can pass to this logistic regression function. So let's run this cell to open the documents here. So we have to scroll all to the up so that we can see the function. So here is the logistic regression function. So if we do not pass anything and use the default value, so we can see that the penalty it is used is L2. So it is using L2 regularization. Okay, the other important parameter is a tolerance. So the value of tolerance it is using is 0.0001. And it is also using another thing, which is C. C is the regularization parameter like the lambda which we used in the regression analysis, but this is a sort of inversely proportional to the lambda. So if C is equals to 1, in that case, lambda is also equals to 1. But if we decrease the value of C to less than 1, then lambda will be greater than 1, because lambda is approximately equals to 1 over C. Then we have fit intercept is equals to true. And the other important parameter could be the solver. The default value of this solver is the optimizer, which is used to find the optimal value of the weights in order to reduce the loss function or the cost function. So this is LBFGS, and maximum iterations are 100. So these are 4 or 5 important parameters. There are a lot of other parameters, but these are 4 or 5 important parameters which we can use for our logistic regression function. So what are these parameters? So this is the penalty, that is L2 regularization, whether you use L1 or L2. So during the grid search, we will pass both L1 and L2, and we will let model to select which penalty is best. So tolerance is very important thing. Suppose this is a very small value, 0.001. So basically tolerance is used to compare the difference of the weight updation. Like suppose after the 10 iterations, when the model is training and try to converge to the best values. So after 10 iterations, if the weight update value is 10, and after the 11th iteration, if it is 9.9, then in that case, the difference is 0.1 or the improvement is 0.1. So that 0.1 value is greater than the tolerance. So whenever the difference in the weight updation value for the logistic regression model will be greater than the tolerance, we have to keep update the weights until we reach the value which is less than the tolerance. So if the weight updation is 0.00001, that is there are 40 after the decimal place and then 1, then that weight updation value will be less than tolerance. In that case, we will stop further optimizing our weights. So the tolerance value will tell us when to stop the optimization of the weights and the bias value. So these are the few parameters which we can give to our model. So let's provide all the possible combinations. So here I am providing fit intercept is equals to either true or false. Penalty I am using L1 and L2. Here I am passing quite a few values for the maximum iteration. I am passing the different value of a C. I am passing the different value of the tolerance, and I am passing solver equals to saga or liblinear. Now the question is why I am passing only these two solver. So if we go back and check our document, so the option for the solvers are, so these are the penalties, and here we have the options for the solver. If we can see here, so the solver are L1, L2, and so this is the important information about the solver. So why we are using saga and liblinear? So these are only two solver out of these six solvers which allow us to pass both L1 and L2 as a parameter for the penalty so that model can select the best. If I use this function, it will not allow me to pass L1. It use either L2 or none. Similarly, all the other are also uses either L2 and none. So if I use liblinear and saga, they are allowing me to pass L1 and L2 as a penalty parameter so that model can select the best. So here we have passed all the necessary parameters to the model. Let's run this cell so that model can select the best parameter out of these possible combinations. So it may take few seconds because there are a lot of parameters like maximum iterations. We have passed the 5 value. Similarly, there are a lot of values for C. Penalty is L1 and L2. Fit intercept is equals to true or false. So we can see that model has selected best possible input parameter. The value of C it selected is 0.2. Okay. The fit intercept it has selected is true. Maximum iteration it has selected is 100,000. Penalty, it is going to use L2, solver saga, and value of tolerance is 0.1. So we can see that by using grid search cross validation, we have selected the best possible parameters with the help of our logistic regression model. And we use these parameters and we see these parameters in the document of logistic regression by passing the logistic regression function into the help function. So if we pass any function to the help, we can see the complete documentation. That is what kind of parameter to be passed to this particular model. So we can see that for logistic regression, these were the important parameters, and we provide the logistic regression all the possible combinations of these parameters, and our logistic regression model has selected the best possible value for these parameters. So these are 1, 2, 3, 4, 5, 6 different parameters. Now, it's time to use these parameters to get the prediction from the testing data. We have the predictions, and now it's time to print the classification report. So I will import the classification report from sklearn.matrix, and here it's time to print the report. So we can see that we have 100 testing samples. So these are the number of testing samples. Out of these 100 testing samples, 54 belongs to class 0 and 46 belongs to class 1. So the value of precision is 89% for class 0, 87% for class 1, and it is 0.88 or 88% on average. Similarly, we have accuracy value of 88%, and we have the precision and recall value and F1 score, all value is equals to 0.88 or 88%. Now here what we can do is that from sklearn dot matrix we can import confusion matrix F1 score. So let's calculate F1 precision recall other than the classification report. So here in classification report we have the values of all these parameters, but we can calculate them again with the help of this function accuracy score, the precision score, the recall score, and F1 score. So here we can see that these values are approximately equals to 0.88, that is 88%. So we can also see our confusion matrix. So these are the parameters, that is the weight, size, and font for the confusion matrix. Let's generate the confusion matrix. So we can see that this is our confusion matrix for this problem, and these are the value of true negative, true positive, this is false positive, and this is false negative. So we can also plot our ROC curve here, and ROC curve is the plot between the false positive and true positive. So we can see that its value is 0.8888%, which is equal to the precision value of the model, that is 88%. So in this lecture, we learn how to perform grid search cross validation with the logistic regression. So it was very, very important project, so that we learn what are the possible values of the parameters which we can pass to the logistic regression function, and similarly what are the possible combinations that can be provided for this parameters, so that a logistic regression model can select the best possible parameters so that the model performance can improve. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture.